nodal centers have connected right now, everybody. That is just I want to test. Engineering College Bikaner, is it connected? No. Next, JECRC.
Yes, sir. Good morning, sir.
Good morning. Is it connected now?
Yes, sir.
Okay. Everything is clear. Audio and video, everything.
Yes, sir. We are audible.
Okay. Next, what about Rajasthan Institute of Engineering Technology? Avdesh.
Hello. Good morning, sir.
Good morning. Avdesh, is it Avdesh Dixit?
Sir, RIT Jaipur.
Okay, RIT Jaipur. Okay. Is it clear everything? Audio, video?
Yes, sir. Yes, sir.
So that we can start na session. Next, fourth one, Panipat Technology. Panipat.
Yes, sir. Yes, sir. Yes, sir.
Okay. Yes, sir.
Yes, sir.
Okay. Now let's start the session. Okay. Today, that is Thursday, fourth day of this total short-term training program on new manufacturing technologies. Today we have expert, that is Dr. Joy Prakash Mishra, who is coming from NIT, National Institute of Technology, Kurukshetra. So he has done his PhD from Indian Institute of Technology, Roorkee, and even MTech also from Indian Institute of Technology, Roorkee. So he has done his PhD in electrochemical honing of gas, super finishing of gas. Today we have this expert, Dr. Joy Prakash Mishra, to deliver lecture on first 10 to 11:30. He will be delivering the topic on hybrid machining processes, and later that is 11:30 to 12 tea time. After tea break, again he is delivering second lecture, that is ECM, ECD, EDM, and WEDM and EDC. So this is the topic he will be covering today from morning for the morning section. So now I kindly request Dr. Joy Prakash Mishra to deliver a lecture on the above topics. Thank you. Now we can start the session. Okay. Thank you.
It's not working.
इसी में है पूरा आपका?
पूरा फुल रही है।
इसको कॉपी कर लेना है।
कॉपी है
इस पे कॉपी किया फोल्डर में?
हाँ।
अच्छा। ओपन विथ इसमें करके देखेंगे ये क्या पिक्चर नहीं करना है। वो सपोर्ट नहीं कर रहा क्या वो मैं वो 2016 का है क्या वो MS ऑफिस
MS I think
हाँ तो सब अच्छा चलो हम उसको आफ्टरनून देखेंगे ना।
So, very good morning, all of you, and thank you, Professor Raf, for my brief introduction. So, today we will discuss about hybrid machining processes. If we check the date when this process has been started, it is really difficult to find out, because this manufacturing processes or the machining process or the metal removal process is starting from the very primitive age, and it has been practiced by the ancient peoples for making weapons or tools. For example, this is a making of hand axes during Stone Ages. So the left one photo is for the primitive tools used by the ancient people, and the right one is basically this picture shows the evolution of the processes. These are the primitive one, and now the present day scenario, that this one This one is the micro shaft of diameter 15 micron. I think if you know the diameter of hair, human hair, it is near about it ranges near about 20 micron to 15 micron. That means this shaft is the diameter of this shaft is lower than the diameter of the human hair, and that can be produced by only micro turning. And this structure is made by micro WDM. So now this is the present condition of any machining process, and this is the evolution of machining process from the primitive to present day scenario. So today we'll discuss all about that hybrid machining process, and before that we will discuss the basic of machining processes and how the transformation occur from machining to or traditional machining to the advanced machining process and advanced machining to hybrid machining process. So take a look of my content of the presentation talk. My presentation talk will start with the introduction part, in which we discuss about the basic definition of the machining process. And after that, we'll discuss the advanced machining process or the necessity of advanced machining process, why actually it is needed. And then moving on, hybrid machining process, we'll discuss about hybrid machining process, its classifications, its types, its typical examples. And then we discuss electrochemical honing in detail. Basically, electrochemical honing is the electrochemical based hybrid machining process. And further, we will discuss about the future scope or the scope that can be carried out for future research work. So moving on. So this is my objective of this presentation, to share my knowledge and findings of hybrid machining process, to encourage the research community to carry out research in this field, to mature these processes, to make them commercialized. This hybrid machining since last decade, these hybrid machining processes are emerging in the different industries, and they are going to replace all the advanced and traditional machining processes day by day. But main problem with these processes are that these processes are not. It is very much difficult for us to get a proper setup or proper machine equipment for this hybrid machining process. If we wish to carry out any hybrid machining processes, we have to fabricate it in your lab or in your in-house. You have to develop in-house. So it is the main problem with this processes, this group of machining processes. And so my presentation talks is to give a details understanding or my findings, so that you can carry out your research work in this field, or to make these processes commercialized. So moving on, take a look of the basic definition of the machining process. Machining is basically a subtractive time manufacturing process in which surplus materials is removed in the form of chips to impart desired shape, size, and finishing to the final object, using a suitable cutting tool and using a suitable relative motion between cutting tool and workpiece. This definition is very well known to us, and main highlight of this definition is that subtractive type, surplus material is removed, suitable cutting tool, and suitable relative motion. We all know that manufacturing process basically, that is the process or the method of value addition. That means we have to convert the raw material into some finished product by some value addition. That is the definition of manufacturing process. And we all know the manufacturing processes are classified in 4 groups: additive, subtractive, formative, and assembly type. Additive means that final object or the finished product will be obtained by addition of material. For example, casting, for example, rapid prototyping. Next, subtractive type manufacturing process, in which we remove the extra metal, and we'll get the final product. For example, machining operations or machining processes. Then formative type manufacturing process, in which we will get the final product by plastic deformation of material. For example, rolling, forging, extrusion, etc. And then assembly type, in which you get the final product by joining of materials. For example, adhesive joining, welding, riveting, etc. So coming to the definition of machining process, it is basically a subtractive type manufacturing process, because the final object will be obtained by the removal of material or a removal of extra material. Main highlight is the suitable cutting tool. If we check the images, that we are very much popular, well known about these operations. This operation is turning operation, this is drilling operation, and this is milling operation. If you take the example of turning operation, when this tool comes in contact with this rotating workpiece, it compresses the workpiece and produces severe plastic deformation, and material is removed by shearing action. And this phenomena can only be possible if the tool is harder than the workpiece. Suppose if we wish to turn a steel rod, we have to choose a high-speed steel cutting tool, high-speed steel as cutting tool. But it is really difficult for us to cut a steel rod by using a cutting tool that is made of aluminum. So the basic motto, and the same story is same for the drilling and milling. The basic tagline of machining process is that the tool should be harder than the workpiece. And this set of machining process which follows this tagline, the tool should be harder than the workpiece, are known as traditional machining processes or conventional machining processes. So moving on, there are some photographs which indicates a international event, and it is, I know you all know about it, it is obviously Second World War. And this is the most detrimental after effect of Second World War, that is the explosion of Hiroshima. So besides this nightmare of human civilization, this Second World War compelled us to think in a different way. And this is the sum of the colorful after effect of Second World War. The generation or development of new technological industries like automotive industries, aerospace industries, satellite industries, marine industries, etc. Up to Second World War, the conventional or traditional machining were very much popular. But as these technological industries are developed after Second World War, and the products or the components are used in these industries are basically employed in a very hostile environment. For example, satellite. The component used in the satellite of space is really the environment of the space is completely different from the atmospheric environment, and therefore we need some new or non-traditional materials. So we can say that the development of advanced technological industries like aerospace, automotive, and satellite is accompanied by the development of very hard, high-strength, difficult to machine materials such as stainless steel, superalloys, titaniums, and ceramics. So we need some new techniques, because the traditional machining processes have the tagline that tools should be harder than the workpiece. But now these materials, the hardness of these materials is harder than the material used in traditional tools. So we have to move on and we have to think in a different way. So if we produce complex geometries and maintaining high dimensional accuracy in such materials, really found really difficult by conventional machining processes. These problems necessitates the exploration of advanced machining processes. These advanced machining processes are characterized by higher power consumption and low MRR, and they are chosen for their special capabilities to produce extremely complex part and machine uncanny materials. Okay. So this is the main boundary conditions of any AMP or advanced machining processes. If we wish to cut, AMPs can be cut for any material or can be used for any material, but it should be used for which materials which are really difficult to cut by traditional processes. Suppose it is really, if we wish to cut or if we wish to turn an aluminum rod, it is really, aluminum is very soft material. You can easily cut aluminum material by any conventional machining processes like turning. If we wish to cut titanium, then we can go for advanced machining processes. So this is the main criteria or main boundary condition of using the AMPs, that AMPs can be used for only for complex or tricky geometry or difficult materials or difficult to cut materials, because these AMPs are associated with high power consumption, high initial cost, and low MRR. The MRR of AMPs in most of the cases is lesser than the conventional techniques. So normally advanced machining, in case of traditional machining processes, the fundamental concept is that tools should be harder than the workpiece. So we have to change this concept, or we have to use some new energy sources or new technique to remove the material. So which type of energy sources is used? On the basis of that, advanced machining processes are classified in 4 groups: mechanical type, chemical type, electrochemical type, and thermoelectric type. Mechanical type, in which material is removed by erosion of high velocity particles, for example AJM and USM. AJM stand for abrasive jet machining and USM stand for ultrasonic machining. Then comes the chemical group, that in which the material is removed by corrosive action of reagent, for example chemical machining. Then electrochemical type, in which material is removed by ion displacement or anodic dissolutions, For example, ECM and ECD. ECM stand for electrochemical machining and ECD stand for electrochemical drilling. And finally, thermoelectric type, that in which material is removed by melting and vaporization. For example, EDM and EBM, electric discharge machining, and EBM stand for electron beam machining. So this is basically a list of AMPs. Those are very much popular nowadays in industries. On the basically this classification is there, and their mechanism and material removal is there. For example, mechanical, if it is mechanical type, then the mechanism of material removal is erosion. For example, AGM, USM. If it is electrochemical type, the mechanical mechanism of material removal is ion displacement, and electric current will be used as energy sources. Similarly, for chemical, it is corrosive agent, and thermoelectric, it is either electric spark, high-speed electrons, powerful radiation, ionized substance, or ionized substances. This table basically is showing a comparative study of process capability of different AMPs. In case of, if we look the MRR, it is very low, very much lower than the traditional processes. The MRR of PAM is highest, that is 75,000 mm³ per minute, but the surface finish is very rough. Surface finish is not up to the mark. Okay, so if we wish to use any advanced machining process for our application, we have to choose this wisely. So these processes, these advanced machining processes are very much popular up to 1970s or 1980s. But during that time, it was found that these processes are also having some drawbacks. So, for example, I think we are all known about the ECM process or electrochemical machining process. In electrochemical machining process, an anode is there, that is workpiece. Workpiece is connected to the positive part, and tool is connected to the negative part, and a gap is there in between tool and negative tool and positive workpiece. That gap is basically inter-electrode gap, and that is provided to avoid the direct metal to metal contact or to avoid the short circuit. When this gap is flooded with proper electrolyte, the electric circuit completes, and due to that, ECM process or electrolytic dissolution process starts. But main problem with that, in case of electrolyte, normally aqueous solution of any salt or any basic or acid is used as electrolyte. So if we, during the process, this aqueous solution of the water is also dissolute in H plus and OH minus, and as a result, the oxygen is evolved out at the anodic part or workpiece part. This oxygen reacts with the workpiece or metallic workpiece and produces a metallic oxide layer, and this layer is basically a passive. This layer is basically an insulating layer. So this layer further stops the process, or to further acts as an insulating layer on the workpiece and stops the process. So this is the main problem with the ECM process. The ECM, in case of ECM process, the MRR is good because material is removed by the material is removed in atomic scale. So surface finish is good, but MRR is good because rate of dissolution is high. But main problem with that, after few cycles, it stops due to generation of this metal oxide layer or insulating layer. So we have to remove these drawbacks, and to remove these drawbacks, or to eradicate these problems of advanced machining processes, hybrid machining processes are conceptualized by combining two or more than two AMPs, two or more than two advanced machining processes, or AMPs or advanced machining processes with conventional machining processes, so that we can add up or we can sum up the benefits of both the processes, both the constituent processes, and minimizes the drawbacks of different processes. So basically, this hybrid machining process can be characterized by 1 plus 1 is equal to 3 equation. If normally 1 plus 1 is equal to 2, but we are adding two processes, so we add already sum up the benefit of both the processes, and plus one thing is there, that is we also eradicate the drawbacks of both the processes. That means 1 plus 1 is equal to 3, not 1 plus 1 is equal to 2. So moving on, this is a typical example of hybrid machining processes, that is electrochemical drilling, in which, or electrochemical grinding, in which we combine electrochemical machining process and mechanical grinding. The electrochemical dissolution phase of electrochemical machining combines with mechanical grinding or mechanical abrasion phase of mechanical grinding, and as a result, we will get the final object. So basically, hybrid machining processes or the constitute on the basis of constituent process, the hybrid machining processes are classified in two groups. First one is that both the processes or both the constituent processes are directly involving material removal. For example, electrochemical grinding. Electrochemical grinding is a combination of electrochemical machining and mechanical grinding. Electrochemical machining and mechanical grinding both removes the material from the workpiece. Second classification, that is one process directly removes the material, while other process only assist by making the machining environment favorable. For example, ultrasonic assisted abrasive flow machining. Abrasive flow machining is basically a mechanical type advanced machining processes in which material is removed by the flow of abrasive slurry. Okay, so we add ultrasonic assistant as a performance multiplier of the process. So in this process, ultrasonic assisted abrasive flow machining, in this hybrid machining process, ultrasonic assistance never participate in material removal, but it actually multiply the performance of abrasive machining. So this is the main classification of hybrid machining processes. First one, where both the processes removes the material from the workpiece, and second one, in which one constituent process removes the material and other acts as performance multiplier. This diagram showing the complete list of hybrid machining processes which are very much popular nowadays in research labs only, not in industries. Okay, the round one are the constituent process, and the elliptical one are the resulting hybrid machining processes. For example, this ECM process or electrochemical machining process combines with mechanical honing or the conventional honing and produces electrochemical honing or electrochemical finishing as hybrid machining process. Similarly, lapping combines with ultrasonic machining and produces ultrasonic assisted lapping. This ultrasonic assisted machining combines with AFM and produce ultrasonic assisted AFM or ultrasonic assisted abrasive flow machining. Here in this case, in ECH and ECF and USL, the one constituent process is advanced machining process, the ECM is advanced machining process, while this honing is conventional machining process. But in case of USAFM, USM is also ESM and AFM both are advanced machining processes. So similarly, US ECM is there, ECDM is there. ECDM is formed of ECM and EDM. Then ECDG is there. In ECDG, three constituent processes are there. First one is the ECM, second one is EDM, and third one is grinding. This is known as electrochemical discharge grinding. So these hybrid machining processes are developed to minimize or to reduce the drawbacks of or the problems we experience during advanced machining processes. This is a schematic diagram of the process principle of electrochemical discharge machining. Basically, main problem with the electric discharge machining is that in case of if we wish to carry out electric discharge machining, the main limitation is that the workpiece should be conductive in nature. So it is really a big problem for us because we cannot use this setup, or you cannot use this machine setup, or we cannot use this fundamental concept for the non-conductive material. So we club electrochemical dissolution with electrodischarge erosion and produces a new technique, that is electrochemical discharge machining, which can be which is capable to machine whether it is conductive or whether it is a non-conductive material. This is abrasive electrodischarge grinding. Here electrodischarge erosion is combined with mechanical abrasion to improve the performance of electric discharge machining process. Electrochemical discharge grinding. In this process, three constituent processes are there: electrochemical dissolutions, mechanical abrasion, and electrodischarge erosion. Then ultrasonic assisted lapping, where ultrasonic vibrations combines with mechanical abrasion and produce a new or hybrid technique, that is ultrasonic assisted lapping, whose characteristics or whose the process capability is far better than the both the constituent process, that is ultrasonic vibration or ultrasonic machining, and mechanical abrasion. Then ultrasonic assisted electrochemical machining, that in which ultrasonic vibration combines with electrochemical dissolutions. Then ultrasonic assisted electric discharge machining, that is in which ultrasonic vibration combines with electro discharge erosion. And laser assisted electrochemical machining, in which laser assistance is added to the electrochemical dissolution to improve its performance or process capability. So this is the highlight of main so far. Actually, main highlights is that we already talked about main difference between AMPs and the conventional machining. The problem with conventional machining is that this tagline is there: the tool should be hidden on the workpiece. This concept is completely gone in case of AMPs or advanced machining processes. In advanced machining processes, the energy sources used for material removal is completely different from the conventional one, and therefore that tagline is of no use in case of AMPs. I already discussed about the definition and classification of hybrid machining processes. Okay, the necessity of hybrid machining processes: basically hybrid machining processes are required or basically are needed to minimize the drawbacks of AMPs. And we already talked about different hybrid machining processes which are very much popular in the research lab only. So this is the main highlight we already discussed about. So now moving on, we will discuss about the electrochemical honing process in detail. Basically, electrochemical honing, a typical example of hybrid machining processes. It is an electrochemical based hybrid machining process. We did a lot of work on electrochemical honing, and I'm here to share my findings and the knowledge on this field. So starting for the basics part, that is ECH basically combines two processes, ECM and mechanical honing. ECM stands for electrochemical machining, in which material is removed by the anodic dissolutions, and mechanical honing. Mechanical honing is basically a conventional type, subtractive type manufacturing processes. In ECH, ECM provides faster material removal because in case of ECM, material is removed by the anodic dissolutions, so the MRR is higher. Stress-free surface, as in case of ECM, tools never comes into contact with the workpiece, so the workpiece surface is completely stress-free, and good surface finish. In ECM, material is removed by the anodic dissolutions, or material is removed at the atomic scale. As a result, we'll get a good surface finish on the workpiece. That is up to micro or nano level. Okay. The mechanical honing in ECH, mechanical honing provide control generation of functional surface. Distinct cross-hatch lay pattern, because continuous simultaneous rotating and reciprocating motion is there, and as a result, the resulting lay pattern will be of cross-hatch. This lay pattern, or this cross-hatch lay pattern, is having a good typological property because the oil retentivity capacity of this lay pattern is higher. So if any component is going to use in any where typology is really a big issue, typological phenomena is big issue, then we can go for honing process or electrochemical honing process. Then residual stresses induced surface and ability to correct macrogeometrical errors. So start with the first constituent process, that is electrochemical machining. This is based on the Faraday's laws of electrolysis. This is advanced machining processes. Here tool is connected to, I already discussed about the electrochemical machining. Here tool is connected to the negative part of the power supply, and workpiece is connected to the positive part of the power supply. And a gap is there in between tool and workpiece to prevent the direct metal to metal contact or to prevent the short circuit. And this gap is known as IEG or inter-electrode gap. When a proper electrolyte is there or proper electrode is flooded in this gap, this electric circuit completes and anodic dissolution starts. This is the fundamental concept, or this is the process principle of electrochemical machining process. So these are typical reactions. Some of the reactions are there. If we use iron, if we use iron as workpiece, copper as tool, and NaCl aqueous solution as electrolyte. And this is the final outcome, the precipitation of ferric hydroxide and evolution of hydrogen gas. These are typical examples, typical advantages of an application of electrochemical machining processes. That in ECM, electrolyte removes dissolution products, metal hydroxide, heat, gas bubbles generated in interelectrode cap. As continuous flushing is there, continuous flushing of electrolyte is there, and therefore it can free the machining zone from this type of from metal debris or any gas bubbles or heat. ECM can process complex cavities in high strength materials and produce biofree surface. In case of ECM, the material is removed by anodic dissolution, so material hardness is not a limitation. So you can process any material, whether it is very hard or not. But the limitation is that material should be conductive in nature. No, in ECM, no direct contact between tool and workpiece, which results in no tool wear. Material is removed in atomic scale, obviously produces good surface finish. Various industrial techniques have been developed on this basis of ECM concept. For example, electrochemical drilling, electrolytic drilling, safe tool electrolytic machining, etc. These are typical examples of electrochemical machining, electrochemical process-based machining processes. First one is the electrochemical drilling. Second one is electrochemical jet drilling, where a conductive jet is used to drill the workpiece, and this process can be used for superalloys also, and it produces a hole of aspect ratio near about 50 to 80. This is electrochemical hole reburing, and these are defined typical. Basically, the components can be finished by electrochemical machining process. Now moving to the next constituent, that is honing. Honing is a subtractive type manufacturing process in which materials are removed in the cutting action of bonded abrasive skeins. It is used to improve the form, dimensional precision, surface quality of workpiece under constant surface contact with the tool. Honing is applied after precision machining. Honing is basically the MRR of honing, or the basically material removal capability of honing is very low, and it can be used after grinding process for only to improve the finishing or the macro geometrical errors. Normally, three types of honings are very much popular in industries. First one, that is longitudinal stroke honing, or frequently are referred to as honing, short stroke honing, or designated fine honing, and super finishing or gear honing. So longitudinal stroke honing used for connecting rod holes, brake drum, and cylinder liners. Short stroke honing used for crankshaft or rotor shaft, and gear honing are used for provide a precision finishing to the gears. So coming to the basically combination of both these processes, that is the hybrid machining process, that is electrochemical honing, which combines both these processes, and as a result we'll get 5 to 10 times faster than conventional honing, this MRR, and 4 times faster than grinding, and the surface finish up to 0.05 micrometer can be achieved by this process. Electrochemical honing is started in the 1963, but it is accelerated in the year of 1981. But the main problem with this process is the development of the design of the tooling system. This process is generally used for finishing either internal cylindrical surface, and that is known as or termed as ECH of cylinders, or gears, and that is termed of ECH of gears. Coming to the process principle of this process, in step 1, in ECH process, ECM process and honing process combines. The electrochemical dissolution phase combines with electrochemical machining phase, and mechanical abrasion of honing phase combines with it and will get the final output. In step 1, cathode is there, workpiece is there, and a large amount of asperities and peaks and valleys are there, and a proper electrolyte is flooded in between cathode and the workpiece, or in the gap between cathode and workpiece. Now, as the electrolyte or anodic dissolution starts, the metal is removed from the by ion displacement. Metal is removed from the workpiece, and the asperities will be lowered down. But due to the formation of metallic oxide, or formation of, as aqua solution is there, and water will be dissolved in hydrogen and oxygen, and this oxygen will react with the workpiece, there is a chances of formation of metallic oxide layer, and this layer is basically a insulating in nature, and this layer this layer will cover the workpiece surface and make the workpiece non-conductive. So as a result, the ECM process will stop. Now honing or abrasion action comes into picture, which scraps the metal oxide, this insulating layer, from the high spot and produces fresh metal for further electrochemical dissolutions, and thus these honing actions accelerates the process. So basically in this process, we already told that AMPs are having some drawbacks, and we combine some other process with AMPs to produce high beam measuring process, so that we can add up the benefits of both the process, and we can remove the or eradicate the drawbacks of constituent processes. So here ECM is having some benefits, for example, good surface finish, high MRR, but the problem is that formation of insulating layer, and we have to remove that drawback, and that's why we add honing action or scrubbing action with it, and thus we remove the problem, and we get a better process, that is electrochemical honing, whose capability is many times better than the electrochemical machining process or mechanical honing process. This is typical ECH or electrochemical honing tool that is used for ECH of cylinders. So coming to the next part, that is ECH of gears. We are very much well known that gears are vital element of any mechanical industries to transmit power and motion efficiently and economically. The transverse rate is almost 99%. And annually 2-3 billion gears are consumed worldwide, with turnover running into 7 billion euros. So gear teeth surface should be smooth and error-free, so smooth and noiseless power motion transmission. If there is any discontinuities in gear teeth profile, we should encourage the chances of fatigue failure and reduce the service life or the lifespan. So gear finishing is the only criteria, or the gear finishing is the only remedy for this. So we applied or employed this technique, ECH process, to improve or to provide a finishing to the gears. Conventional gear, there are so many conventional gear finishing techniques like gear grinding, gear saving, gear honing, and gear lapping, but those are costly, time consuming, and having material hardness limitation, because in conventional techniques the tool should be harder than the workpiece material, and therefore there is a limitation of the material hardness. If this material, the workpiece material, is harder than the grinding wheel or the abrasive used for gear honing or gear lapping, then it is difficult to remove the material, or it is difficult to finish the workpiece. Therefore, these processes are really having material hardness limitation. Moreover, it is costly and time consuming. So need some different solution, and for that ECH of gears is there. It is initiated by Capello Bartoglio in 1979. Though the ECH process started in the year of 1963, but ECH of gears has been started in the year of 1979, and after that is accelerated by Chen et al. In 1981. The fundamental concept of both the processes, whether it is ECH of cylinder, whether it is of ECH of gears, is the same. Fundamental concept of the basic process principle is the same, but main difference is that tooling. The tooling of the ECH of gear is completely different from the ECH of cylinders. This is the schematic diagram that's showing the process principle of ECH of gears. In this picture, 3 gears are there. The middle one, that is workpiece gear, the left one, that is cathode gear, and right one, that is honing gear. Now this workpiece gear acts as driver, and honing gear and cathode gear acts as driven gear in this gear train. Now this workpiece gear is simultaneously rotating and reciprocating. Now just take a look of this cathode gear. This is the broader view of this cathode gear. This cathode gear is fabricated by sandwiching a conducting gear between two insulating gear and undercutting the profile of conducting gear, then insulating gear. This undercutting will act as the inter-electrode gap or the necessary gap which will prevent the short circuit. Now this workpiece gear and cathode gear and this gap, if this gap is flooded with proper electrolyte, the electrolyte circuit completes and ECM action starts. But after few cycles, after few runs, there is a formation of metal oxide microfilm on the workpiece. That oxide layer is insulating in nature, which will be removed by this scrubbing action of honing gear, and this honing gear will produce some trace metal for further electrochemical dissolutions, and thus will get a better output. So coming to the process parameters of ECH gears, basically process parameters of ECH gears are classified in 4 groups: power supply related, electric supply related, honing related, and workpiece related. Power supply related parameters are, for example, current is there, pulse of time is there, pulse on time is there, duty cycle, and voltage. Electric supply related parameters are composition, concentration, pressure, temperature, flow chart, flow rate, conductivity, and pH. And type of abrasive particle size, rotating and reciprocating speed, or the ratio of rotating and reciprocating speed are used as honing parameters. Then electrolyte and mechanical properties of workpiece, size of workpiece, and pH comes under this group, this workpiece related parameter. And normally surface integrity aspect of the gears, macro geometry, gear teeth profile, teeth thickness, micro geometrical properties, for example, roughness, process capability, MRR can be used as measures of process performance. Beside this, the typological phenomena or the typological property of gear teeth surface can be used as process performance parameter. So coming to the fabrication part of the experimental setup, that basically this is the schematic diagram of the experimental setup of ECH of gears can be used for spur gear. This experimental setup basically consists of 4 sub-elements. First one is the power supply systems, that consist of this power supply system. This consists of this power supply system and the wires, and then electrolyte supply system that consists of electrolyte chamber, electrolyte supplying unit, heat exchanger, etc. And then tooling systems that consist of this workpiece gear, cathode gear, and this rack and pinion system. And finally, the last one, that is fixtures or machining frame. This is the schematic diagram of experimental setup that is used for bevel gear. Here, 2 bevel gears are used, first one and second one. Here this bevel gear is used as workpiece, and these both are used as tooling purpose. Here that a gap is there. This tooling are basically fabricated by clubbing 2 different gears. One is made of any conducting material. For my case, it is copper, and other is made of steel. And after that, the steel is coated with any non-conductive abrasive particles. So basically, we club cathode and honing in a single tool. Okay. And this is the photographic view of the experimental setup that has been developed in the developed in our lab. Okay. This is power supply unit. This is pump and electric supply units. This settling tank, reservoir is there, heat exchanger is there, because so that we can maintain the temperature of electrolyte, because basically the conductivity of electrolyte is very much responsible for the processes, this electrolyte or anodic dissolution process. And by using this heat exchanger, we can control the temperature, and thus we can control the conductivity of the electrolyte. So heat exchanger is there, flow meter and pressure gauges are there, and this is the basically tool and tooling arrangement, that's motion supply to the tooling. And this is the machining chamber where actual operation will be carried out. Okay, and this machining chamber consists of normally three types of gears: workpiece gear, one cathode gear, and one honing gear. So the broader view of this machining chamber is here. This is workpiece gear. It is made of steel, and this is the combined, or this is the fabricated tooling, that the middle one, that is shown in red or brown color, that is made of copper, and it will be act as cathode gear. And the upper and lower, that white one are made of basically steel, and for after that it is coated with non-conductive abrasives. Non-conductive abrasives. So this workpiece gear acts as driver, and this abrasive coated gear will be act as driven. Okay, there's a gap in between. This profile of the copper gear is the diameter of the copper gear is a bit lower than the diameter of this abrasive coated gear. As a result, during the motion or during the process, this copper gear never comes into contact with the workpiece gear. Okay, now if we provide a proper electrical supply in between this gap, the electrolyte circuit completes and the process starts. There is a rack and period arrangement is there, so that we can move that block in left side or right side, so that we can accommodate different sizes of gears. Where if we for application, if we require some gear of larger diameter, then we have to move this block. So basically this part is made to make it more commercialized. Rest of the part of the fixtures and the machining chambers are made of either any non-conductive material. For example, this work table is made of bakelite. This work chamber is made of Perpex, so that we can minimizes the chances of getting current shock. This is the machining chamber that has been developed for electrochemical honing of helical gears. Here, this workpiece gear is helical one. This part is used as honing gear, and this is the cathode tool. Here, copper gear, that is conductive gear, is sandwiched between two bakelite gear, and undercutting the profile of copper gear, then bakelite gear. So when during the motion, this workpiece gear will provide the motion to the bakelite gear, not the copper gear. So a gap is in between there, that will be act as inter-electrode gap. And this is the broader view of the developed cathode gear. A bush is there, that is made of brass, to provide the necessary current supply to the shaft and to this copper gear. This is a machining chamber developed for the electrochemical honing for bevel gears. Here two blocks are there, and a slot is there on this slideway, so that we can easily move these blocks and accommodate different sizes of gear if it is required. Now coming to the experimental outcome. This is basically a comparative study of both the processes, or three processes basically. This is the unfinished profile. This is the bevel gear that is made of simple milling cutter or conventional milling cutter, and as a result, that feed marks are there, bars are there, and surface finish or the surface profile is not so good. Okay, now we use this bevel gear as a workpiece material for the ECH process. And after the process, we'll get two different surfaces. The first one, that is glass surface, that is finished by electrochemical mechanical finishing or electrochemical honing, and the rest part, the second part, that is only by abrasion. This is the fabrication setup. That means here cathode, this copper is used as cathode, and only front part of this bevel gear will be finished by electrochemical honing process, and the rest of the part of the second part will be finished by this honing part or honing gear, that means by abrasion. So this thing is tried because we have to compare the process capability of all the processes for milling, for electrochemical honing and abrasive or honing. So there comparison comparative study is there. This glaze part is for electrochemical finishing. This part is for abrasion, and this is the condition of milling. So you can from this figure, it is very much clear that electrochemical honing is a better process to provide precision finishing to the gears. So this is the scan version of gears. This is before the process, and this is after the process. Before the process, the surface is not so good and irregularities are there, and that can be removed or then can be eradicated by the ECH process or electrochemical honing process. Now coming to the surface roughness, this after the process, the surface roughness of the workpiece profile or the workpiece has been carried out by non-conductive surface profiler, and we get that is the 6.8 micron is the before the workpiece. 6.8 micron is the RA value before the processing, and after processing it is 359 nanometers. That means almost 94% improvement in the surface roughness by ECH process that can be obtained. So we can say that this ECH process is obviously a better process for finishing to the to provide finishing to the gears. These are the same micrographs carried out at 500 magnification and 1000 magnification. These micrographs are before machining, before the processing, basically electrochemical honing process. And these micrographs, it is clear from these micrographs that feed marks are there, micro pits are there, cracks are there, and surface finish or surface quality is not so good. And these micrographs are after the of workpiece after the process, and it is clear from these micrographs that the surface quality or surface integrity aspects or surface topographical aspects can be improved by the process, because these surfaces are having less value, less number of these feed marks, less amount of micro cracks or pits. So coming to the advantages of ECH process, this process increases the material removal rate, particularly on hard materials and bar-free action, because we combine ECM process with honing process. So we club the MRR of both the processes, first of things. And here most of the material, almost 80 to 90% of the material is removed by the electrochemical machining process or anodic dissolutions. So hardness is not a limiting factor, because the only limitation is that material should be conductive in nature. It improves the accuracy and threefold increase in abrasive efficiency. In this case, tool never comes in contact with the workpiece, and so no tool wear occurs. So no spark is produced and the temperature generated is low, which does not cause metallurgical changes in the workpiece material. A continuous flushing is there, continuous flushing of electrolyte is there, which removes the generated heat from the workpiece zone. As a result, the working temperature is near about 30 to 40 degrees centigrade, and as a result, there will be no metallurgical changes in the workpiece can be experienced. Less pressure required between work surface and abrasive stones, because this abrasive particle in this process in ECH, in case of honing, abrasives are used to remove the metal, but in this process, ECH process, honing stones or abrasives are used to just scrap the metal oxide microfilm, so not for material removal. So less pressure is enough to carry out the process, and this process is obviously faster and higher material removal rate with reduced horn wear, and it is about 10 times of that for conventional honing and 4 times for that conventional grinding. But obviously this process has some limitations. First one is that the main limitation is that the workpiece should be conductive in nature. First thing. Second is that huge amount of energy is consumed, because there are lots of power supply unit is there, motion supply unit is there, and therefore power consumption is really a big issue for this technique. ECH is more costly than a conventional type because of electrical fluid handling elements and the need for corrosion protection. In this process, Normally salt solution, aqua solution of salt, basic or acid is used as electrolyte, and therefore corrosion is really a major headache. And so here and therefore maintenance, proper maintenance is required so that we can eradicate this problem. Blind holes are not easily handled as through holes. In this process, ECH through holes can be easily finished by this process. For blind holes, it is observed that it is not so capable enough, not so capable. So we can say that this is the limitation of ECH process, that it cannot be properly or successfully used for blind holes. Now coming to the application. In ECH, most of the material is removed by ECM action process, keeps the workpiece cool, free and heat distortion, produces bar-free and stage-free surfaces. This technique can be used for any material, regardless its hardness. Only things that material should be conductive in nature. Presently, most of the automotive industries are trying to use this technique for finishing internal cylinders, and defense institutions or defense research labs are trying to employ this or starting employing this technique, as it will provide better finishing to the internal cylindrical surface, for example, gun barrels. So this process has been started in the year of 1963. That time only this process has been employed for providing precision filling to the internal cylinders. In 1979, the ECH of gears has been started, but till date this process is having huge scope of research, or is in infancy, basically infancy stage. So we have to if we wish to choose this technique or this process as our research career, it is really wise decision. Obviously, this will be a wise decision, obviously. So main future scope is that the mechanism of material removal, or the ratio of material removed by the electrochemical action and honing action, is yet to be discovered or yet to be explained. So main problem is that real-time modeling of the process, or the modeling of the process by finite element modeling or FDM, is really a need proper attentions. Or we have tried this technique for the material of tried this technique in where workpiece material is steel, but that it can be tried for other material, for example titanium, tungsten, or other aluminum material. So lots of scope is there for so that so that we can carry out this process as our future research work. So the key message of this presentation is that electrochemical honing is a electrochemical based hybrid machining process. It is capable to provide micro nano level finishing to the cylindrical surface or gears, and it requires comprehensive study for commercialization in industry. So main problem with this technique is that the setup or the machine setup or the experimental setup is not available in the industries or any research lab. So if you wish to carry out research in this field, we have to fabricate this part. Okay. Or if we order this machine setup for any industry to produce, then it will be cost near about 50 lakh or 60 lakh. But if we wish to fabricate in-house or in-housely, then we can develop it in within 1 or 2 lakh. So it is my suggestion to you, if you wish to carry out this part as your research work, it is better to fabricate this setup, and then carry out the defined experimental work. So this is all about the hybrid machining processes and all about the electrochemical honing processes. Some references are there. So queries are always welcome. Any doubt, queries are there. My mail ID is there. You can contact me through this mail ID if you require. And before that, presently we are working in this technique, that we are trying to club a ultrasonic assistance to the this process, so that we can improve or we can multiply the process performance. This is the schematic diagram. of ultrasonic assisted electrochemical honing process. This is rest of the part is same, only this ultrasonic assistance is there. And before closing this presentation, I wish to show some of videos. This is workpiece gear, and this is tooling, and this is backlight block is there. This rack and pinion is used to move this block. Okay. Motion is supplied to the workpiece. This workpiece is used working as driver, and this tool is here tool is driven. Before that, only rotational motion was there. Now, simultaneous rotational motion and reciprocal motion is there. So this is in dry condition, and this in wet condition when electrolyte supply is also there. This workpiece is simultaneously rotating and reciprocating, and the proper electrolyte supply is there in between gap in the gap or in the electrode gap. The microprocessor controller unit is there to provide the reciprocating motion by using a stepper motor. This is the power supply unit. This is the inlet of electrical supply. This is for helical gear at wet condition. This helical gear is used as workpiece material, which is rotating and reciprocating simultaneously, and electrolyte supply is there in the electrode gap. This is honing tool, that is basically opposite coated gear, and this is cathode gear, which is fabricated by clamping and sandwiching a copper gear between two backlight gear, and undercutting the profile of copper gear, then backlight gear. This is the working of PCH of bevel gas with dry condition. No electrical supply is there. It is not so clear actually due to electrolyte supply, but it is PCH of bevel gear with electrolyte supply. So this is all about the electrochemical honing process. And any queries, any doubts are there, please. Sorry?
What is the material rate?
Material removal rate, actually don't know the exact data. It to remember actually. But it is better than the honing process. Okay, for example, better than the honing process, better than the grinding process.
Since we are
I just can tell you that the same size of gear can be finished by grinding process in 1.7 hours. That can be finished by this process only in 10 minutes. So you can compare that.
the two materials are used, the gear, the two cathode, anode and the cathode is the same type of material.
Can be used. Can be used. But if you use better inorganic dissolution, because copper basically our design and fabrication part that depends mainly on the two or three determining factor. First one is that ability of the material. Second thing is that costing. Okay, on the steel is used as workpiece material here. Okay, we can go for titanium, we can go for tungsten, we can go for other material, aluminum also. But steel is very low cost, cheaper than any material.
That parent material you can use titanium.
Yeah, you can use any conductive material can be used. Yeah. But main problem is that cost is really associated with it, and we are at fabrication part. We are doing some fabrication part, and that's why we need a lot of amount for other purpose, and that's why we choose steel, and that is only 40 rupees kilo. Yeah.
Because then another question is that if you're using steel or something like that, in due course there will be a pumping action, there will be a better removal in the parent materials.
Sorry, I can't get you.
Sorry, we are using the electrode. The materials are connected to a parent material. The rotating part, the media, the hosting gear.
Okay.
Then, if you are in due course of time, this material, this diagram, also called as a diagram because this is the responsibility of make the workpiece, right?
The workpiece gear is there.
Yes.
Okay. One honing gear is there, one cathode gear is there.
So
Now,
this honing gear
yeah.
will take in due course of time, it will be some metal removal will be there, right? Because it is there is a chance of being direct contact because of the
Honing gear is always in direct contact with the workpiece gear. Okay. Honing gear is abrasive coated. Okay. And the obviously hardness of abrasive is a bit higher than many times higher than the steel. Okay. So due course of time, due to corrosional effect of the electrolyte, there may be some chances, but that is very rare.
Of course, if it's contact with capacity, then
That is very rare. Okay. And because we can't use any conductive gear as honing gear. We can't use any conductive gear as honing gear because that will in contact with the workpiece. Okay, and as a result, we have to provide extra current density because then that part will be used as workpiece part and the workpiece surface. So you have to then we need a better power supply unit to minimize that problem and to provide the abrasive section. We just coat the any steel gear by any non-conductive abrasives. Alumina is used. Alumina is used as coating material. No, not partially conductive, but that is not the big issue actually. Anything else?
JCRC Jaipur, do you have any query? Would you like to give any feedback? JCRC Jaipur.
Good morning. Good morning, sir.
Very good morning.
Sir, through your presentation, we came to know that honing gear is made up of bakelite and copper.
No, not honing gear, that cathode gear or the tool.
Yeah, the cathode gear is sandwiched between bakelite and the copper. So my question is, as bakelite is in contact with the steel, so there will be some wearing will be there between bakelite and steel.
It is there, but very rare it is. So not a.
Sir, but the distance will change now. So because of that, potential difference between the cell will change, get disturbed.
Actually,
And what about the MRR issue on MMR, metal removal rate?
Actually, I wish to share one thing. The machining time is only 10 minutes.
Yeah,
So
but still, if suppose if number of if this process is uh, uh, taken into a larger scale, suppose in commercial industry, then if many gears will be produced and honed at simultaneously, so because of that, the process time will increase. Suppose this is if this technique is made commercially, then what will happen? Then how this issue will be answered?
Then you have to choose a better non-conductive material or harder non-conductive material.
What would be the materials, if any?
Uh, you can go for any other thermosetting plastics.
Thermostatic.
Yeah.
And what about the other physical properties like brittleness and all? Will they?
Brittleness is really a matter because you have to form the gear, na? You have to manufacture the gear. So it should be easily formability is there, should be there.
And secondly, I have a little bit doubt, sir. I just want to know that what is the role of honing gear in this? I mean, you have shown that picture,
Okay. Which picture can you?
a setup, machining chamber, and yes, I mean, uh,
This one?
yes, sir, yes, sir. Earlier one.
Okay. If you check the process principle of ECH, na, that ECH process combines both the process, honing process and electrochemical machining process. Okay.
And then what about the wearing of honing gear?
I coming to that point. Okay, just let me finish. Basically, if you check the process principle of ECH, it combines both the process. One is electrochemical machining, one is honing. Electrochemical machining process having some drawbacks. That formation of metal oxide microfilm, and that is insulating a layer, and that covers the metal, basically workpiece surface. So we have to remove that surface so that we can continue the ECM process. That honing gear, basically honing gear is made of a gear that is coated with abrasives. Okay, this abrasive will produce a crabbing action on workpiece and remove that layer so that we'll get fresh metal, and so that we can continue the process, ECM process.
Okay, sir. Thank you, sir. Thank you.
Thank you very much.
Sir, we have a little bit query.
Yes, please.
What about this? If this as per this your process, what is the effect of the tribo corrosion?
What is the effect of?
Tribo corrosion. Yeah, will it affect the tribo corrosion also?
Obviously, but yet to test actually, yet to study. There is a
Okay.
future scope. You can take as a future scope for this part. Okay.
Thank you, sir.
Thank you very much.
White college, so do you have any query? White college. White panicut. RIT Jaipur. So do you have any query? Engineering College Bikaner. Sir,
Okay. Thank you very much. So now we are having, I think, one tea break, and after the tea break, after 30 minutes. So after 30 minutes, then at 12 o'clock, we'll start our discussion with electric discharge machining, electro discharge coating, and well electric discharge machining. Yeah, please. 1 minute.
So,
नहीं फॉर्म भरवा लिए आपने भर दिया ना हाँ हाँ इसमें कर दो। इसमें एडवर्टाइज आ रहे हैं
Let's start.
इस पेपर है क्या पेपर पेपर कोई भी A4 साइज वाला वो बुक का दे दो वो बुक फाइल कर दो वो बुक 1 मिनट हाँ वही
Okay. A very good afternoon and welcome back. So after the tea break, we will discuss about this EDM, EDC, and WEDM. EDM stands for basically electric discharge machining, EDC, electric discharge coating, and WEDM, that's war electric discharge machining. So my presentation talk consists of these steps. First, on the introduction part, in which we discuss about the basic of EDM process. Then electric discharge machining, its capability, its efficiency, and its process principle. Then electric discharge coating. What is the need of basically electric discharge coating? Electric discharge coating basically a modified version of electric discharge machining, and we'll discuss it in detail about how electric discharge coating can be used to modify the electric discharge machining setup for our benefits. And then a brief detail of where electric discharge machining will be discussed, and finally conclusions and future scope. So moving on, in the last session we discussed about the defined aspects of machining and machining processes, and we all know that machining process is a substrate type manufacturing process. So manufacturing, if we take a look of the definition of manufacturing process, and manufacturing process means the conversion of raw material into finished product or some value addition to the raw materials. And for that, we need some energy sources. Okay, if we wish to convert raw material into finished product, beside man, machine, money, we need some energy sources or method so that we can easily convert the raw material into finished product. So this is the basically the thermal energy or the heat energy is the most efficient energy, most easily available energy that can be used by which we can convert a raw material into final product. And the manufacturing process which depends on this thermal energy, those are known as thermoelectric manufacturing processes or thermal related manufacturing processes. But today in this session we will discuss about thermal or thermoelectric type manufacturing processes. So thermal processing are as like machining processes, like conventional machining processes, that there is a classification of machining processes. Like machining processes are added to 3 types: conventional or traditional, advanced, and hybrid. The thermal processing or thermal type manufacturing processes can be classified in 2 groups: conventional and advanced. The conventional thermal processing are characterized by low energy density pulses used for longer duration. That the example are heat treatment, and it is used for the structural transformation. In case of heat treatment, the working temperature or the operating temperature in between melting temperature of the workpiece and recrystallization temperature. For example, annealing. If you wish to carry out annealing process for a 0.8% NITTTRCHD steel, that is 0.8% carbon steel, we have to do? We have to keep the workpiece in the furnace and heat it up above the ostensible temperature, that is near about 800 or 850 degrees centigrade, and keep this workpiece furnace itself without any further heat input. Okay, as a result we will get a slowest cooling rate, and after that we will get coarse perlite as final microstructure. So basically this is conventional thermal process where low energy density pulses are used for a longer duration. The working temperature is low, but the working time is high. The first example is heat treatment, and second one is the welding, where the working temperature is in between T vaporization or the vaporization temperature of workpiece and melting temperatures workpiece. For example, arc welding. Now, these conventional techniques are very much popular in industries, but these are having some undesirable effects. For example, higher heat consumption, because the time duration is high. Sorry, time duration is short, but the temperature is high, and then excessive thermal distortion. This is the main problem. Undesirable structural transformation and inaccuracy. For welding, this inaccuracy is nothing but the defects of welding. Okay, so we're moving on, and we move to the from the conventional to the advanced or unconventional thermal processing, in which high energy density pulses are used for shorter duration. Here, temperature or working temperature is high, but the working time is very low or very basically microsecond. So, for example, this advanced or unconventional thermal processing can be used for machining purpose. Okay, and in which material will be removed by melting and evaporation, and the working temperature is far above the vaporization temperature of the workpiece. So this advanced AMPs or advanced thermal processes having some advantages over conventional techniques. First one is that the peak surface temperature is very high, because in case of advanced type thermal processes, we are using a high energy pulses for a shorter duration. So the peak surface temperature is very high. More uniform temperature distribution, okay, because the heat is provided in a very localized zone, so distribution and temperature is uniform. Greater depth of penetration of heat and the end of pulse. The heat is applied on a localized zone, therefore penetration is very high. Heat is applied on localized zone and the amount of energy is very high, therefore depth of penetration is obviously high, and more precision accuracy. So the advanced thermal processes are more precise and more accurate than conventional types. But this is also having some drawbacks, that it is associated with high capital investment. So okay, we have to, if we wish to carry out some advanced thermal processes, we need some extra amount of money in our pocket. Second one is that very high operating cost. Operating cost is also very high. Tooling system is very costly, and high maintenance cost. Whatever may be the drawbacks, the advantages are more in case of advanced thermal processes, and therefore defined advanced thermal processes are nowadays popular, or nowadays employing in defined industries. Some of them are listed here. First one is the EDM process. Those are basically, this list includes only the advanced thermal machining processes. Okay, first one is the EDM, electric discharge machining, in which high voltage is used as an energy source, and dielectric is a transfer medium, and the mechanism material removal is that bombardment of electrons. Now EBM, that is electron beam machining, where ionized material is used as an energy source, but transfer medium is vacuum, and here also bombardment of electrons are used to remove the material from the workpiece. Now LBM stands for basically laser beam machining, where amplified light is used as energy source. Transfer medium is normal atmosphere, and bombardment of photons basically used to remove the material from work surface. And then PAM and IBM is there. PAM stands for the plasma arc machining, and IBM, that is electron beam machining. That is, in PAM, ionized material is used, transfer medium is plasma, and bombardment of heated ions. Among these 5 machining processes, or 5 advanced thermal machining processes, PAM is having the highest MRR, but surface roughness is not so good. Okay. So now we move our concentration or focus to the electric discharge machining. This is the first machining process listed here, electric discharge machining. So this process basically initiated by B.R. Lazarenko and N.I. Lazarenko in the 1943, and they, though the spark discharge was first observed by the Sir Joseph Priestley in 1768, but till 1943 it is not used for machining purpose. B.R. Lazarenko and N.I. Lazarenko is the first one who used this spark to remove the material from the difficult to machine materials. So this is the fundamental concept of the process principle of EDM process. This is tool or tool electrode, you can say. This is workpiece. Okay, a gap is there in between tool electrode and workpiece, and a dielectric fluid is flooded in between tool and workpiece. Tool is here connected to the negative part of the negative pole of the power supply, and this workpiece is connected to the positive pole of the power supply. This is the broader view of this machining zone. Now, as a sufficient potential difference is established between tool electrode and workpiece, the electrons start moving from electrode to the workpiece. That is called cold emission of electrons. Okay. Now, as the electrons accelerates or gain after gaining sufficient velocity, as the electrodes move towards workpiece, it ionizes or it will break. If the potential difference is higher than the breakdown voltage of the dielectric fluid, these electrons ionize the dielectric fluid or break the dielectric fluid into positive ions and electrons. Positive ions and electrons. And as a result, a column of or a narrow ionized column will be formed in the closest distance between tool and workpiece. And this is known as avalanche of electrons. That is seen as spark, and due to the spark a huge amount of heat will be generated, and the temperature rises near about 10,000 to 12,000 degrees centigrade. Using this heat, the material or the workpiece will be melted and vaporized, and as a result we will get the final outcome. This is the process principle, that is cold emission of electrons, and then electrons accelerate towards anode, breaking of dielectric fluid into electrons and positive ions, then narrow column of ionized dielectric fluid, that is known as avalanche of electrons, rising of temperature, generation of temperature, that is 10,000 degree to 12,000 degrees centigrade, and owing to this temperature, the melting of vaporization of electrode materials, and finally molten metal is evaporated by mechanic blast, causing craters on the both electrodes. Okay, a proper dielectric fluid is there, or dielectric fluid, flushing of dielectric fluid is there, which will remove the mechanical metal debris from the machining zone for better process capabilities. Now coming to the experimental setup, this is all about the process principle of EDM machine. Now coming to the experimental setup of EDM. Experimental setup of EDM consists of mainly 4 sub-elements. First one is the power supply unit that will provide the pulse DC supply across the tool workpiece gap. Then dielectric system, which will provide flow of dielectric at a desired pressure and flow rate and to recirculate the dielectric. The servo system, which will maintain the constant tool and workpiece gap. And finally the tool electrode, that will basically, EDM process is the copy paste process. If we wish to produce a surface, we have to choose the same surface on the tool. If we wish to cut a basically this is a copy paste process, and we can easily produce the replica of the tool on the workpiece. So basically tool electrode is a replica of the shape to be produced in the workpiece. So now coming to the second element, that is power supply. It is not a big issue for any EDM setup. The main issue is the dielectric system, because it is main responsible factor for the process capability. So dielectric system, basically these are the necessary properties of any dielectric systems, that it should be electrically non-conductive, or it should be act as insulator between tool and workpiece until the breakdown voltage is reached. Okay, after breakdown voltage it will be act as conductive. It will be act as conductive to act as flushing medium to remove the material by products from the tool workpiece gap. After the machining process or after the spark, the metal will be removed from the workpiece, as in metal will be removed from the workpiece, and we have to remove those metal debris from the workpiece zone, and therefore continuous flushing is there. Flushing is required, which is provided by dielectric system. Third operation of dielectric system is to act as coolant to remove the heat from. Due to spark, a high temperature is there in the working zone, and we have to remove that heat from the working zone so that the microstructural transformation can be minimized in the workpiece. And for this purpose, dielectric system is also used. and these dielectrics are used as coolant also. Should not react with the machine elements. Okay, if dielectric is in corrosive in nature, we can't use it because it may react with the machine element and may increase our maintenance cost. Absence of toxic vapor, it is for safety purpose of the user. Should not cause fire hazards, it is also for the safety purpose of the users, and economically suitable, is obviously of low cost. So there are some examples of dielectric. Those are normally used for EDM process. First one is the hydrocarbon oils, kerosene, silicon-based oils, deionized water, and gas. In most of the industries, kerosene is used as dielectric fluid for EDM process. Now coming to the tool electrode, that is the third element of our setup. The desirable characteristics are high electrical conductivity. As the EDM process, the limitation of EDM process is that the tool and workpiece both should be conductive in nature, and therefore the first desirable characteristic of tool electrode that the electrical conductivity should be high, because this is the most responsible factor for your which should control the process capability of EDM process. Then thermal conductivity, so that it can easily dissipate the heat, generated heat. Then high melting temperature. The tool electrode should be having high melting temperature so that the tool wear rate would be minimum. Easier manufacturability, because EDM process is a copy-paste process. We can easily produce the replica of the tool. If we wish to produce any shape in the workpiece, we have to produce the same shape on the tool. So the manufacturability or the machinability of any material should be good enough so that we can easily produce a shape on the tool. And obviously cheapness, obviously that means low cost. So selection criteria of tool electrode are that MRR, the material removal rate of the process, wear ratio, that is the ratio between MRR, the material removal rate, and tool wear rate, ease of shaping the electrode, easy manufacturability, and finally the cost. There are typical examples of defined tool materials. Tool materials are broadly classified in two groups, either metallic electrode or metallic tool material and non-metallic tool electrode. Metallic electrode, the list of metallic electrode consists of copper, brass, copper tungsten, copper boron, chromium copper, tellurium copper, aluminum alloy, silver tungsten, and steel. Copper, brass, copper tungsten, copper boron, chromium copper, and tellurium copper. Basically, these are having good good electrical and thermal conductivity and good machinability. So you can easily shape into you can easily form into different shapes. This aluminum alloy is also very soft material, and you can easily machine it into different shapes. Now silver tungsten. The silver tungsten is basically an alloy of silver and tungsten. Silver will provide the required conductivity, electrical conductivity, and tungsten will provide the required strength, high melting point. A steel is there, which is very easily available and low cost. One non-metallic tool are normally used, that is graphite. Graphite is having very good thermal, electrical conductivity. Now coming to the servo system, this is the main sub-element of any machining setup of EDM. This is used to maintain the predetermined tool workpiece gap. A gap should be there in between tool and workpiece so that spark can be generated, which is the main energy source for material removal. So that maintaining of that gap or controlling of that gap is done by servo system. The gap is sensed through the average voltage across it, and the voltage is compared with a preset value or initial value, and the difference is used to control the servo motor. Basically, a feedback or closed loop control system is there to maintain this gap. Okay, and it also depends on the dielectric flushing system. If dielectric flushing system is not proper, then it is difficult for the dielectric flushing system to remove the metal debris from the machining zone, and which will provide a error value to the control system, and as a result it is difficult for the servo system to maintain or control the tool workpiece gap, and for that we need a proper dielectric flushing system. So we can use any servo motor for this purpose. Other alternatives are, if you use to fabricate any setup or fabricate any EDM machine in your lab, you can use stepper motor. This is basically EA. This is a cheapest solution for you. So you can use stepper motor for this purpose. This is basically other alternative if you wish to fabricate any setup of EDM. So these are process capability of EDM process. Drilling capabilities, 127 to 6.35 range, 6.35. This is in all data are in millimeter. So hole diameter that can be produced is minimum hole diameter that can be produced by EDM processes, that is 0.127 millimeter. That means 1 to 7 micrometer. Aspect ratio that can be obtained is 10 to 30. Hole depth is up to 50. Then minimum taper, maximum number of holes that can be drilled simultaneously is 200. Minimum angle of inclination, that is 20 degree. Then cutting capabilities are there. Up to 50 mm thickness can be cut by this process. Finishing capabilities, surface roughness of 0.8 micron can be achieved by this process. This EDM process, basically in EDM, most of the material is removed by the catter, in the form of catter, and due to spark, and therefore the surface roughness that can be achieved by the process is not so good like ECM process or the other finishing processes. So this is mainly a problem for EDM process, but 0.8 up to 0.8 micron up to 8 micron surface roughness can be achieved by this process. So there is no chemical damage, okay, because we use a dielectric that is not having any corrosional effect. The mechanical damage, that is up to 25 micron because a overcut is there, and thermal damage, that is 25 to 20 to 50 micron. Economic aspect, coming to economic aspect, initial investment obviously very high. Tooling and fixtures cost is also high. Power consumption cost very low. Tool consumption cost is high tool wear because that spark is generated and it will remove the metal from both workpiece and tool, and therefore a high tool wear is there. Where is there? Okay. So in case of environment, in this aspect of environmental, that is safety is normal problem. Safety is not a big problem. Toxicity, normal problem, and contamination of machining medium is a normal problem. So environmental aspect of safety is not a headache for us. Main problem is the economy or the investment. Now coming to the material application, EDM can be used for any material, but that material should be conductive in nature. So all electrical conductive metals and alloys can be machined by this process. Super alloys can be machined by this process. It is very difficult for the traditional process or conventional machining process to machine super alloys because the super alloys is having high hardness, high strength to weight ratio, and a low machinability. But in case of EDM, metal is removed by the high temperature. The temperature ranges near about 10,000 to 12,000 degrees centigrade. So it is not a problem for us if we going to cut super alloys or if we going to machine super alloys by using EDM process. Tungsten carbide and hard carbides can also be machined by this process. This is the basically beauty of this technique. And refractory material. If refractory material which are having very high hardness and very high brittleness can be machined by EDM process, but the limitation is that this refractory material should be conductive in nature. Now coming to the shape application, different various shapes can be produced by this process. 2D profiling can be done, 3D contouring can be possible, stamping of tool dies, making blind complex cavities, drilling of various hole shapes, micro holes, through cutting, non-circular holes, and cutting of narrow slots can be done by this process. So this process is a very useful process, and these processes are now very much popular in industries, mainly tool die industries. Okay. So this is all about electrode discharge machining process. Now a question is there. This is the basic question is there. If both electrodes are made of the same material, okay. In case of ECM, what do we do? Why do we did that? Workpiece is made of steel and cathode is made of copper. But in most of the cases in EDM, we use the same material for workpiece and same material for tool electrode. So now question is that if both electrodes are made of the same material, then which electrode erodes faster? And the answer is positive electrode. Now why? Because the momentum with basically the momentum with which stream of electrons strike the anode is much more than that due to the stream of positive ions impinging on the cathode, and therefore the heat generated on the positive electrode part is higher than the negative electrode part, and as a result positive will be electrode will be erode faster. And another thing is that pyrolysis of the dielectric fluid. Pyrolysis is a phenomena that creates a thin film of carbon on the cathode. As due to spark, a huge amount of temperature is generated on the machining zone, and due to that temperature, the hydrocarbon will break, and a thin film of carbon on the cathode will be formed. This phenomenon is known as pyrolysis. So these two phenomena are there for which are the responsible for the eroding of positive electrode faster, or faster eroding of positive electrode. So our main problem that EDM process can be used for any material, any conductive material regardless its hardness. But main problem with this process is that cost. A high initial investment is required. So now our motto is that we are having a EDM machine and it costs near about 40 lakh or 50 lakh. So it can be used only for EDM purpose, or we can use it for other purpose also. So we think this way and tried something so that we can use this EDM process for other purpose also. So use this concept, this benefit. Basically, this beauty of this process, the pyrolysis of the dielectric fluid, or making of or creating of thin film of carbon on the cathode for our benefit. But how? By using or by developing electrode discharge coating process. This is basically a modified version of EDM process, or electrode discharge machining process, where electrode discharge machining is used for coating purpose, not for material removal purpose. In case of EDM, electrode discharge or spark are used to remove the metal from the workpiece. But here, this discharge or this spark is used to produce a coat on the workpiece surface. So this is the fundamental concept or the process principle of the electric discharge coating process. Here, tool electrode is there, and electrode is connected to the positive part of the workpiece. In case of EDM process, most of the time, tool electrode is connected to the negative part of the workpiece, negative part of the power supply, and workpiece is connected to the positive part of power supply. But in case of electric discharge coating, the tool electrode is connected to the positive part of power supply, and workpiece is connected to the negative part of power supply. Basically, then in case of positive electrode, the metal removal will be more. So we need more metal removal from the tool so that we can use that material for coating purpose. So in case of electric discharge coating, we just modify the EDM process and change the polarity of the electrode and workpiece. So here electrode is connected to the positive part of the power supply, positive pole of the power supply, and workpiece is connected to the negative pole of the power supply. Now dielectric fluid, a gap is there in between electrode and workpiece. The proper dielectric flushing is there in between electrode and workpiece, and as a result EDM process starts, basically electric discharge process start, and generation of heat, a high temperature of heat. But this most of the material will be removed from the electrode. And for example, if we use titanium or tungsten electrode, the Ti will be removed. Okay, and this Ti will be react with the carbon that is already decomposed for the hydrocarbon that is used as dielectric fluid. So, and this as a result, and finally that will segregate on the workpiece surface as a titanium carbide or tungsten carbide layer. This titanium carbide or tungsten carbide layer is very hard and good for corrosion resistance property and good for wear resistance property. So we tried this technique for our purpose and having some good result, having some good publication. So I'm going to share these things with you. So the total process or total study has been carried out in different steps. First one is the workpiece selection. An aluminum alloy of size 20 mm, 20 mm and 5 mm has been selected as workpiece material because it is having some commercial and industrial importance in aerospace, transportation and automotive industries. Aluminum alloys nowadays are very most popular, basically popular metal after steel. So aluminum alloy is used as workpiece here or selected as workpiece here. Surface modification of aluminum alloys using hard material like titanium improves its crack resistance, wear and corrosion resistance property and thus its lifespan. So we have already carried out the chemical analysis of aluminum alloy and it is basically a alloy of manganese and chromium, and these are the chemical analysis of the chemical composition of different elements present in the aluminum alloy. Now coming to the tool fabrication part. Basically, we need a large amount of metal to be removed from the tool electrode. So if we use a tool that is made from casting, then it is really difficult to get metal deposition. And therefore, to solve our purpose, we use a powder metallurgy tool in place of casting tool. So that in case of powder metallurgy, bonding is not so good or not so strong like casting tool, and therefore in this case a powder metallurgy or green compact tool is used so that we can easily get deposition of titanium powder on the workpiece. So a titanium carbide and copper powder of mesh 325, that is minimum mean diameter is 44 micron, were chosen as materials of tool electrodes to realize the coating process of the workpiece surface. This green electrode, tool electrode were prepared by powder metallurgy process, the same process that compacting and sintering and thing, using a 12 mm die and punch assembly. That means our tool is having the diameter of 12 mm. Now we need good conductivity because titanium, we need the coating of titanium only, but we mix copper so that we can improve the conductivity of the green compact tool. If you use only titanium, because powder products are having porous or pores in the structure, and therefore conductivity is not so good. To improve that but in case of EDM or HDC process, we need good conductive material as tool material. Therefore, copper is mixed here with titanium so that we can improve the conductivity of the green compact tool. Now a 12 mm diameter green compact tool is produced, and after that, a 12 mm diameter, that green compact tool electrode were attached to the steel rod. This steel rod is basically used to hold the this steel rod is used for holding purpose in the machine, because this steel rod will be fixed in the machining jaws. Okay, so this green compact tool electrodes will be attached to the steel rods with the help of an electrically conductive adhesive. Okay, so that we can continue the we can make the complete part conductive. Now coming to the parameter selection. Now coming to the third step, that is parameter selection. Normally, basically all the parameters who are related to the EDM process or who are related to the powder metallurgy are responsible for the final outcome, In our study, we only consider peak current, pulse on time, and electrode polarity as EDM related parameters, and coating time and electrode composition and compaction as powder metallurgy related parameter. Okay, only two type of electrode polarity are used, positive and negative. Positive means in which first case where that electrode or tool electrode is used as positive electrode, or where second case where a tool electrode is used as negative electrode. Coating time 1 minute, 2 minutes and 3 minutes. We have tried this process for 1 minute, 2 minutes, and 3 minutes. Peak current 4 ampere, 7 ampere, and 10 ampere. 16 microsecond, 160 microsecond, 260 microsecond are used as pulse on time. Electrode composition, that is 50%, 60%, and 70%. Electrode compositions basically means the ratio of titanium and copper powder. Okay. For 50%, that means titanium and copper powder in 1:1 ratio. If 60% means titanium powder in 60% and 40% is copper powder. If 70%, that means titanium powder is in green compact tool, 70% of amount is of titanium powder, and rest of the 30% is of copper powder. So as the titanium powder increases, the deposited layer or the hardness of the layer will be increased obviously. But the problem is that the conductivity of the green compact tool will be decreased. And therefore we need a optimal solution or optimal findings for this part. Now the compaction. This is compaction. This compaction basically related to the powder metallurgy portion. 200 megapascal, 300 megapascal, and 400 megapascal is used for compaction pressure. If we increase the compaction, the bonding of the powder or the green compact tool will be more, but problem is that the amount of deposition will be less. So moving on, our next part, that is experimental work. So this is the PM tool or powder metallurgy green compact tool that is made of titanium and copper powder after the compacting and sintering process, and this is attached to a steel rod by a electrically conductive adhesive. And this is the final outcome, or this square object, this square part is basically aluminum workpiece of 20 mm, 20 mm, 5 mm dimension. And this part, this is the coated portion. The same size is replicated here. Okay, this is the coated portion. So we have studied the basically the effects of defined parameters on the deposited layer thickness and micro hardness of the layer, and we found that the peak current, pulse on time, and electrode composition. As the peak current, pulse on time, electrode composition increases, the deposited layer thickness increases. Peak current increases, that means more peak current, more amount of machining process, more amount of discharge energy, more amount of discharge layer. That's why discharge layer thickness increases with peak current. If pulse on time increases, that means discharge energy is more, we will get more deposited layer. Electrode composition increases, that means more amount will be deposited on the workpiece surface. And compaction pressure. If compaction pressure increases, it is found that with increase in compaction pressure, the deposited layer thickness decreases. Why? Because as the compaction pressure increases, the bonding of the green compact tool will be increased. Okay. As a result, chances of depositing of metal or coming out of metal from the green compact tool will be decreased, and that's why this deposited layer thickness decreases with compaction pressure. And this is the study where which shows the effect of peak current, pulse on time, electrode composition, and compaction pressure on micro hardness. And it is observed that this micro hardness is increased with increasing peak current, pulse on time, and electrode composition. And the phenomena is the micro hardness decreases with compaction pressure because this micro hardness depend on the thickness of the deposited layer. If deposited layer thickness increases, that means the hardness will be more. Now after experiment, we will come to the sample preparation part. Because we need some microstructural study so that we can check the deposited layer thickness, micro hardness, and the composition of the deposited layer, so that we can establish our finding. And therefore, in comprehensive sample preparation is required. And for that, cutting a wax sample into two pieces. A wax sample is cut into two pieces through the middle of the coating in the traverse direction. We should also reveal the metal transfer. Okay. This is the final outcome after the experiment. So we have to cut in this way. So so that we can easily continue our further testing. So a diamond wear saw with mean diameter of wear being 0.5 mm is employed. Okay. Embedding of wax sample in a bakelite mold, exposing the section area to prevent the rounding of edges during the polishing of workpiece. So that we can easily hold it and easily we can carry out the polishing process. Then grinding and polishing has been done. So grinding of the wax sample with in the grinding will start it from the grinding disc, and then we start with the emery paper that is ranges from 120 to 100 mesh size emery paper, and then polishing of the ground wax sample with water-based diamond solution with diamond size ranging from 9 micron to 1 micron, and then finally finish polishing by electropolishing machine, okay, which will be carried out with the help of silica gel, and that is particle size is 0.05 micron. And after the polishing process, we will use 2% hydrogen fluoride solution to etch this wax sample. Normally, etching is done to basically focus the grain boundaries so that it can easily, if we place the wax sample after the etching, if we place the wax sample on at the microscope, we can easily find out or we can easily indicate the grain boundaries, because grain boundaries are having high activation energy and they are ready to chemically corrode up by this type of etchant. Now coming to our testing part. This deposited layer thickness was measured on an optical microscope. An optical microscope is used to check the deposited layer thickness, and a micro harness control unit and loading condition of 200 into 10 to the minus 3 Newton is used to check the micro harness values. This is the photographic view of the deposited layer. Okay, this darker one is the deposited layer, and the lighter one or in white color or in gray, this is gray color, that is deposited layer, and that a white one, that is base metal. Okay. This is the EDX analysis of the wax sample after the process, and before wax sample you can check the chemical analysis of the aluminum. It is obvious that only in case of aluminum only aluminum or manganese or chromium is there, but after the process or after the EDC process, when we carry out EDS analysis of the workpiece sample, we found that peaks of titanium and copper is there. That means a layer is deposited, and that layer contains the titanium and copper. Now coming to the micro hardness study, it is found as the distance from surface increases, the micro hardness values decreases, because at that part after 150 micron or after 100, you can say after 100 micron, the micro hardness value is almost uniform, because after 100 micron the deposited layer thickness is up to 100 micron, and after 100 micron this is base metal, that why the hardness is uniform. If we check this part, this is the deposited layer, so you will get highest hardness value on the top surface. As we move downwards, we will get lower value of hardness, and in base metal zone we will get a uniform value of hardness. And it is obvious from this plot that the hardness values goes down from as the distance of surface increases, and after 100 micron it becomes uniform. Okay, this is for base metal. Now coming to the same analysis of scanning electron microscope analysis. This is basically surface at the top surface, and this is after 100 micron after the deposited layer, and that why this deposition is there, but base metal is also there. This part only deposition layer is there, but this part deposited layer and base metal both are there. So this is basically the modified version of EDM, or we can use the EDM process, or it is used the EDM process is used for coating purpose, so that we can basically meet the cost of the initial investment of this machine setup. And so this process is basically in infancy stage and having huge scope for future research. Okay, so some of them are listed here. First scope is that it is a very practical technology having good prospect in various industrial application, because the process is economic and does not need special requirement. If you are already having a EDM machine, we can carry out this process. Okay, so we can try defined metal, defined workpiece, and we can produce a core corrosion resistance, wear resistance coating on any workpiece material. Next future scope is variation in metal powder. Here titanium and copper is used in different ratios. So beside titanium, tungsten powder can be used, or other metallic powder can be used to produce some hard coating. Mesh size can be different. Here 326 mesh size is used. We can go for other different mesh sizes. Different material here, workpiece is used as aluminum is used as workpiece material. So we can, by using this technique, we can coat beside aluminum any other material, for example copper, for example steel, or other material, for example titanium. Study of tribological and corrosional behavior deposited layer needs proper attention. During our study, we already discussed about the micro harness of the workpiece, or micro harness of the final outcome. But tribological properties and corrosional behavior is really a determining factor for this process capability of this technique, and therefore the study of tribological and corrosional behavior needs proper attention. And finally, commercialization of the process. I'm already told about this. The problem with this advanced or hybrid machining processes is that these processes are yet to be commercialized. Those are very much popular in research labs or research institutes, or among the researchers of different premium institutes. But it is really really difficult to get a setup, a machine setup, or ready-made setup, or ready-made concept in industries. So we have to commercialize this process. We can, if it is possible, then we have to commercialize this process for further industrial application. So this is all about electric discharge coating. Now moving on to the next part, that is wear electric discharge machining. And discharge machining is another extended version of the EDM. And just before ending my lecture or ending this session, I just wish to give a brief introduction or a brief idea about what is wear electric discharge machining, and basically a present scenario of this technique, and what type of work can be done, what type of work can be carried out in this process. So aerospace industries, automotive industries, tool and die industries, medical and marine industries require advanced materials, okay, because they are component used in the hostile environment, and therefore we require some new and non-traditional materials like super alloys, titanium alloys, and we need some machining techniques so that we can easily and cost effectively we can machine these materials, and therefore we need some new technique or new concept in the machining field. So wear electrode discharge machining, an extended version of the EDM process, can meet this requirement, and it can easily use for this process can be used to produce complex shapes or tricky shapes in the very hard or difficult to machine materials. So WDM is electro-thermoelectric type advanced machining process. In WDM, the removal material due to melting and vaporization, like EDM process. The fundamental concept of WEDM or EDM is the same. The difference is that in case of EDM, different types of tools are used, as the tool electrodes are used. But in case of wear EDM, wear is diameter of 0.5 to 3.3 millimeter is used as tool. Okay, a gap is between workpiece and wear, that is 0.025, that ranges 0.025 millimeter to 0.05 millimeter. So this is the process principle of WDM process. This is workpiece part. Okay, a proper dielectric flushing system is there. In most of the cases in WDM, deionized water is used in place of kerosene, which is used in EDM. Okay. So workpiece there, dielectric flushing system is there, pump, filter, ionization chamber, and deionized water is there. A wear guide and wear pulley is there for continuous feeding of the wear. Okay, a gap is there in between. This is the diameter. This is the broader view of this part, missing zone. This is the wear diameter, and this is workpiece. A gap is there that is known as spark gap. Okay, there. Rest of the process principle or rest of the concept is same as that of EDM process. Similarly, that this is obviously this ware is made of conductive material. Either normally copper or zinc ware is used. Molybdenum ware is also used as tool. Say rest of the principle is same. These advantages of WDM is that it generates high surface finish and accuracy, can machine any complicated profile. So basically the surface finish and accuracy depends on the diameter of the wear. If wear diameter is the wear diameter ranges it is from 0.5 micron, 0.5 mm. So we can get a gap or we can get a cut of 0.05 mm also. So as a result, we can produce high surface finish accuracy by WDM process. WDM basically depends on in WDM machine, we can cut any profile, whether it is complex shape, whether it is tricky shape, we can easily cut by WDM process. Because the main fundamental concept is that if we check the working condition or working culture of the WDM, it is there that we have to provide the CAD model, basically CAD model of the shape to be produced. Okay, if we can use different softwares to produce that CAD model, and if we provide that CAD model to the WDM machine, WDM machine can reproduce that shape on the workpiece. As a result, any complicated profile can be produced by WDM process. Less wastages and rejection. Okay, stress concentration work materials is negligible because never tool or tool wear comes into contact with the workpiece, and therefore no stress concentration is there. Small batch production including prototypes can be economically machined. The time utilization of WDM is high and it can continuously work throughout the day. We can use a WDM machine for the whole day and produce a large number of workpiece, large number of products, and therefore this machine is very useful in industries. But both, like other advanced machining processes, this WDM is also having some limitation. The material removal rate is slow, but in comparison to the conventional techniques, if we compare the material removal WDM with advanced machining process, then it is far better. But if we compare the material removal rate of WDM with traditional machining processes, then it is slow material removal rate. It can machine only conductive materials. Basically, this is the limitation of all the three types of machining process, whether it is EDM, whether it is EDC, or whether it is WDM. The workpiece should be conductive in nature regardless of its hardness. Next, it is not applicable on large workpieces because we use a machining chamber, and that machining chamber is having a fixed dimension. So if we use to cut some large workpiece, we need some large size of machine. Okay. Formation of liquor layer and hedge, right? Heat affected zone. A huge amount of energy is generated, or a huge amount of heat energy is generated as a working zone that ranges, the temperature ranges near about 10,000 degrees to 12,000 degrees centigrade. As a result, there is a huge chances of formation of recast layer and heat affected zone, which will basically which will create a phase transformation or microstructural transformation of the workpiece surface, which will basically control the metallurgical or mechanical properties of the workpiece. So this is really a issue for us, really big issue for us basically. And last one is the wear breakage. This is one of the problem that if we wish to cut some hard material or powder products, green compact products, then wear breakage is a basically very essential problem. Very essential problem. But this wear breakage this wear breakage problem can be minimized by by finding the optimal setting of parameters, but cannot be completely avoided. Now coming to the application of WDM, WDM having huge applications in different fields. For example, medical field, aerospace field, automobile industries, general industries, and tool and die industries. But presently, this technique is widely used in tool and die industries. Almost all the tool and die industry having one or more than one number of machines in their shop floor. These are typical applications of WDM process. These components these components are manufactured by WDM process. You can cut gears, spline, or simple fins, bevel gears also by this process. You can easily cut miniature gear that having outer diameter below 10 millimeter by this process. Now coming to the research status, most of the, if we go through the literature available on this field, it is available that most of the work has been carried out on steel, because steel is on steel. But if we check that only 5% amount of publications are on safe memory alloys. So if anyone is to carry out his research career on this field, he can choose safe memory alloys as his workpiece material. Because super alloy is there, which is having only 18% of work. Now coming to the super alloys, that most of the work has been carried out on Inconel, okay, but Hast alloy and Monel having low amount of work. So if anyone wish to carry out research work or carry out this field as his research or PhD work, he can took this Hast alloy as his workpiece material. Now coming to the future scope, it is evident from the past research work the WDM process is mostly employed for cutting operation. Though this process can be used for other processes like state turning, step turning, or taper turning. So we can modify the WDM setup for solving these type of problems like state turning, step turning, or taper turning. Normally, square cut or wrap cut are done by WDM process. But besides this, WDM is a huge capability and can produce complex geometries like gears, spline, and curved surface. Some of the work are presently going on WDM of gears. They are trying to produce some miniatures gears by WDM. Okay, if we go for, but if we if we wish to shift our focus from circular gear to non-circular gear, then I think this is the best option for non-circular gears. If we wish to cut non-circular gear or if we wish to produce non-circular gears, then WDM is the best process. Past research work focused on the machining of war metal. It is already told that most of the work were concentrated in the field of steel, machining of steel alloys, aluminum alloys, or composites. WDM difficult to machine materials, namely super alloys, titanium alloys, and safe memory alloys requires proper attention. Okay. The past research work highlights the influence of input process parameter, namely pulse on time, servo voltage. Effect of other input parameters also should be studied so that we can easily finalize the optimum value of different parameters so that we can get good experimental outcome. In detail study of contribution of individual input process parameter are required proper investigation. The EDM process, mechanism of material removal and wear breakage in case of difficult to machine material is not well established. And finally, the typological and corrosional behavior and surface integrity aspects of the WDM machine parts are not elaborately discussed in literature. So there are some of the future research work or future trained for research that can be carried out in the field of WDM. This is obviously another some of them are already here. That is mathematical theoretical model of response parameter, application of defined optimization techniques, and other modification or other extension of this technique, that is dry or near dry WDM. Okay, day by day we are moving from basically normal machining processes to the green machining processes. That means minimizing the use of coolant or dielectric or lubricant. So we can go for dry or near dry WDM so that we can minimize the cost of dielectric fluid. We can minimize the if problems of dielectric fluid. We can minimize the we can basically omit the use of dielectric systems, and we can use by this we can easily cut down the cost of the machine. So this is another extension of this process, the die or near die WDM, in which compressed air or mist is used as dielectric fluid. And compressed air and mist are very you can get it in very low cost, so you can cut down the machining cost also. So this is all about WDM process, EDM process, and EDC process. Thank you very much. Any queries, any doubts?
We are using EDM process for coating, right?
It is modified, huh?
It's a modified version, but if you are using the, what is the advantage than the usual typical that we are using the typical single processing without supporting rollers that is used?
There are basically there are lots of coating processes are already there. For instance, sputtering is there, PVD is there, CVD is there. But if you check, the cost of the EDM machine is very much lower than the PVD and CVD. First of things is that. Okay, we are having EDM process for cutting purpose or machining purpose. So that machine can only be used for single purpose, or it can be used for multi-purpose. So that is the main motto. We are having that beauty that pyrolysis phenomena is occurred during the EDM process. So use that beauty, or we basically take the help of that beauty so that we can coat that also. So if you are having a EDM machine, you can use it for cutting purpose, you can use it for coating purpose. No need to purchase a sputtering machine that costs near about 1 crore or 2 crore.
Have you got any methodological advantages rather than the cyanide processing and cyaniding and nitriding, everything is there? Have you got any methodological advantage?
Not basically cyaniding, nitriding are case hardening process.
Yes.
Okay.
Surface hardening, to an extent.
Yeah, this is case hardening process. This is coating process. This is different thing. This is case hardening. This is coating. Case hardening means is that a layer is that is a layer of the material or workpiece is hardened. But in case of coating, an extra hardened layer is provided on the workpiece. So basically, this process is in basically we are studying this thing, and we are doing some work on this basically this field. But main problem is that yet to be worked. That is typological study is yet to be done in this part. Yeah.
Then lubricant also.
Not lubricant. That is frictional test, wear test. Because beside those tests, we can't say that this layer is really useful for us. We are getting that some deposited layer is there of thickness 100 micron. It is okay. We are getting a higher value of micro hardness. This is okay. But if we're talking about the application, then we have to go for frictional test and wear test. And that part yet to be done.
Friction test and?
Wear test, wear measurement can make it.
Then another question that what about the surface finish of this EDM coating, right? It's not removing of the metal. It's also you are applying it. So what about the surface finish?
Surface is not good. Surface is not good. Not good. Because the deposition is because this in this present scenario, this process is not well established or not well optimized. That's why the distribution layer, deposited layer is not so uniform. That the surface finish is not so good. You can say that poorer than the EDM process or WDM process. But we are working on it. So one day I hope we'll get some good result.
Any query from JCRC, or would you like to give any feedback? JCRC Jaipur.
Hello.
Hello.
Yes, sir. We have a query.
Yes. Yes, please.
Yes, yes, sir.
So, what is the role of reverse polarity in electrocharge coating?
What is the role of electrode polarity?
Reverse polarity. मतलब you said like
Okay, okay.
that tool material will be. Uh, I mean, you showed that process parameter slide now.
Okay, okay. 1 minute.
There you have shown that.
Coming to your point. 1 minute.
Yeah, this slide, yeah. The role of positive and negative parameters. Why we have selected these two? I mean, I have a doubt little bit.
Okay. First of all, we take the example of EDM process. Okay.
Yeah.
Before starting the EDC process, a question is there that if both electrodes are made of the same material, then which electrode erodes faster?
Yeah, you told the positive electrode will wear.
Electro
So,
Positive electrode will erode faster, and why? Because the moment of electron is higher than the momentum of positive ions. One thing, and pyrolysis effect. Okay.
by the use of this paralysis effect, you basically we generated the theory. I mean, basic theory of coating.
Yes.
So,
Basically,
we have reversed the polarity of the EDM machine, and then it will start acting like a electrode discharging machine. Oh,
actually,
sorry,
it's
electrode
coating.
discharging coating machine.
Yeah, coating machine.
Then, why we need to change the polarity again to for the process parameter? My question is for that. I mean, if you're doing electrode discharge coating, then we have to select the that electrode polarity should be
No,
negative,
no,
I think.
that is not changing. Basically, that is for only for study purpose. Okay.
Oh, uh, okay, sir.
Anyone can raise the question that it may be positive, that positive electrode or negative electrode may provide better result, and for that we have to check all the things.
But if we reverse the polarity, then it will act as a electrode EDM. I mean, it will act as a electrode discharge machining instead of electrode discharge coating.
No, 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 not at all.
So that that's
Actually,
what I
problem is that what we need. We need removal of material from tool or removal of material from the workpiece. If we need removal of material from workpiece, then that is EDM, electric discharge machining. Okay. Okay. If we reverse the polarity in case of EDM, we also then that case also you'll get some material removal. Okay. But that case tool wear rate will be more.
okay, yeah.
Okay.
Okay,
In when we check both the process, in both the process we will get some coat. Okay,
okay.
but problem is
Thank you,
that
sir. Now I can got your point.
okay,
Okay.
okay, 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 okay. Thank you. Anything else? Any doubt? Any query?
RIT, do you have any doubt?
हाँ सनी सर बैठे हैं जवाब दीजिए।
हाँ, इसको बड़ा डाउट है ये
अरे नहीं चल रहा है यार देखो
RIT, sir, if you have any query, you can ask.
इस पे अब बोलो
Sir, नहीं.
Okay.
White College, sir, do you have any query? White College?
I'll fight. No. No, thanks, madam.
Okay, thank you. Engineering College, Bikaner, sir, do you have any query? Engineering College, Bikaner.
Okay, thank you. Thank you very much.
Copy कर. Yes. Folder and technology.
Okay.
Now we'll have a lunch break and we'll reassemble again at 2:15. 2:15. Thank you. 15:15:15.
ठीक है 12.60 होता है इसमें 60 बोल दो
इसलिए
घड़ी डालो जो मिनट घड़ी घड़ी चली है ना वो जितना चलती है उसकी रेटिंग ही कितना खा सकती है 1/12 1/12 में मल्टीप्लाई किया वो उसी का शॉर्ट फॉर्म है तेरा तो गलत नहीं होने गलत नहीं करा मैं कह रहा हूं कि मैंने यही फंडा लगाया था मुझे पता है इसी से आया है ना मैं बता ऐसे तो 5 मिनट में क्वेश्चन सॉल्व हो जाता है और गया वाला जो गदा बैठी जो पूरा जल्दी में बढ़ गया ये घंटे के लिए एक बारिश में चल रही है मिनट के 1 मिनट 1 सेकंड के लिए तो दोनों को रिलेटेड किया मैंने दोनों में लिखना चाहिए रिलेटिव लिखना चाहिए दोनों के आपस में मूव एक साथ कितने रिलेटिव स्पीड में बन गई जब दोनों एक साथ चलते तो रिलेटिव स्पीड बात करें तो वो रिलेटिव की 11/12 ये मेन ऑब्जेक्टिव है 11/12 तो ये अपनी रिलेटिव स्पीड आ गई ठीक है ना अब अपना मेन अपने क्या पता है स्पीड बराबर का रेजिस्टेंस को मैं होता है यहाँ पे डिस्टेंस मतलब वो आपकी डिवीजन ठीक है ना अपने क्या निकालना है टाइम तो निकालना है कि उसको कितने बचे थे ये तो निकालना है तो अपने क्या किया टाइम बराबर का डिस्टेंस अपॉन स्पीड तो डिस्टेंस अपॉन स्पीड क्या रिलेटिव स्पीड दिया है रिलेटिव स्पीड क्या किया तो सीधा बस जितने डिवीजन सॉल्व करके उसको 12/11 किया तो मुझे टाइम देगा स्पीड मल्टीप्लाई बाय टाइम जो डिस्टेंस हो गया हां टाइम हो गया डिस्टेंस अपॉन स्पीड टाइम और डिस्टेंस 12/11 इनटू डिस्टेंस हो गया डिस्टेंस कैसे आएगा वही डिस्टेंस मतलब जो डिवीजन वो कवर करती है वही तो मिनट अब मुझे पता कैसे चलेगा ये काम जैसे मैंने तेरे को ये क्वेश्चन बोला 4 से 5 निश्चित कितना होगा 4 से 5 हां 0 है रेफरेंस में देखा 4 की गणित को 4 अब वो कॉन्सेप्ट 4 डिस्कस करेगी तब फिक्स है तो अपने डिवीजन का लेगा 4 बचा कितने डिवीजन कवर की तो डिवीजन मैं यहीं से लेता हूं रेफरेंस से कितने 20 डिवीजन से कवर की सीधी सीधी सी बात है तो अब मेरे को पता है कि डिवीजन में लेते हैं अब रिलेटिव स्पीड मेरे को पता है कि 1/रिलेटिव स्पीड तो मैं यहां पे एक बार 11 बार था 12/11 कर दिया into 20 ठीक है ना 12/11 into 20 ये कितना है 240 240/11 क्या तुम 22 20 21 और ये कितना है 20 9 ठीक है अपने रिमाइंडर भी करेंगे 9 रहेगा सही बात है और ये अपने इसको क्या बोलते हैं क्वेश्चन तो ये अपना हो गया इसको फॉर्म लिख लो किसे नो बता हेलो ये एक नो बता क्या ना ठीक है ना क्वेश्चन बराबर रिमाइंडर अपॉन हां इसी नो बता क्या कोई 11 बात है एक बार क्या 9 रिमाइंडर बता इसी नो बता क्या हरीश लंच खत्म होने टाइम आया क्या आया बताओ अरे क्या हुआ नहीं बढ़िया नेटवर्क काम नेटवर्क कर रहा काम करते आउट टू लंच लंच कर लिया आप लोगों ने वो तो बता रहे 4 फिर आप वहां पे लंच खाए तो और ये है वो मोबाइल मेरा मोबाइल इसको बोल सकते हैं 5 कहते हैं चार्ज पे लगा 21 मिनट है मतलब 20 मिनट हां 5 मिनट में 9 बजे गिरा आपको मैं ये आंसर मेरा है तेरा बिना काम चला गया मेरा ही है इधर मेरा है जा रहे हैं अब ब्रेक नहीं यार तैयारी हो रहा है और उधर बैठ जाते हैं कब निकलोगे क्या तो दिया मदन पानी बोतल
तो तेरे में एक्सटर्नल में था ना, एक में तो एक्सटर्नल में था तेरे वाले में तो तू कहाँ था? हाँ तो तू कहाँ था? तो अरे तो कहाँ था वो तो पूछ रहा हूँ। अच्छा उसमें तो उस टाइम छुट्टी कर रखी थी ना, तो वैसे बट जब मार्क्स बनाए गए तो तूने बनाए थे, तो बाद में तूने बनाया ना आने के बाद मार्क्स तो। अरे यार सारे की कौन पूछ रहा है, तेरे तूने बनाया ना, तूने कौन सा बच्चे नंबर बनाए थे आने के बाद? बैठ जाना मत कहीं, ठीक है? अभी कितने तक तो कौन सा तो बैठेगा, सर्टिफिकेट चाहिए क्या है? कितने बज रही है अभी? 3 साढ़े 3 बजे तक बैठना। आपको लंच करा तो दो यार क्या करा रहे हैं सर मैं मेल करके आ रहा हूँ बस ना, ये सर शुरू हो गया, हो जाएगा तब 1 मिनट लगेगा।
डायरेक्टर सौरभ भारद्वाज को लिखना है डिजाइन सॉल्यूशंस प्राइवेट लिमिटेड इसका सौरभ भारद्वाज लिखना है लिक्रेटिव डिजाइन कोई नई चीज
So how much time it will take? Yes. You have videos also?
पूरा एक मशीन का वीडियो है।
हाँ, yes. यूज करके आप अगर आपको कुछ प्रॉब्लम आती तो आप फोन बोल दीजिएगा, ये फोन कर देंगे।
I will not support it. Then some make some notes.
Okay.
Yes.
think it is better here.
Okay, good. आप अपने हिसाब से करिए. Good afternoon, friends. May I have your attention, please?
Can you the center can reply?
Are you able to listen us?
Hello.
Good afternoon.
Good afternoon, sir.
Good afternoon, Ji. Yeah. Shall we start?
Yes, sir.
Yes, sir.
Okay, thank you very much. Once again, good afternoon. Friends, today we have with us Mr. Sanjeev Bhardwaj. He will be giving lecture on micro machining, and he has done work in. We have called one company person for your benefit, so that you have a practical knowledge about the micro machining. Mr. Bhardwaj has more than 20 years of experience in this field. So, and he's expert in this. Today he will be demonstrating you some machines also. He will show you the demonstration of some machines also. That how the micro machining works. We have one company called Micro Tools. We will be telling about their features, that what latest features they have added in the new machines actually. So I welcome Mr. Sandeep Bhardwaj for this lecture and thanks him for giving his valuable time. Thank you very much and welcome, sir.
Thank you. Thank you. A very good afternoon to all of you. As sir has already introduced me, my name is Sandeep Bhardwaj, and I'm working in the field of CNC machines, which are the most latest technologies they have today. And further, I'm associated with the CAD/CAM industry since last 20 years now. And today we will be covering a session which is a very latest technology, already adopted by most of the institutes in India, and largely they are being used in the research level. The technology which is known as micro hybrid machining center. So I will be covering that.
Will you please share that? आपको बता दिया है, अब share करनी होगी.
Okay.
अभी जो है ना वो स्क्रीन जा रहा है जिसमें हमारी फोटो आ रही थी.
Okay.
अब ये स्क्रीन है.
अब यही करना है. Alright. So today topic will be hybrid micro machining technology. So this is the agenda. We will be covering all these aspects, like what is micro manufacturing and why hybrid micro manufacturing is required. And we will be covering the construction of a unique micro machining center, which is a patent product, and we will be covering the illustration and benefit of hybrid processes. I'll definitely show some samples which we have already made out of that, and largely the application areas in industry and in education side both. And there are some accessories required as an add-on. And finally, a very brief introduction of our company, Micro Tools. It is basically a Singapore-based company, and they are the founder of this machine. So, what is micro machining? This is basically a scientific definition of micro machining. Micro machining is a general term used to indicate a collective form of all the process technologies used for machining of microstructures and microsystems. So this is only a basic scientific, we can say, definition of this micro machining. But as of now, like everybody can recognize what is it. So in our daily life, we are utilizing each and everything which are, the most of the thing which are made of the micro. This is a small, example of micro manufacturing, a ballpoint pen. I hope everybody recognized. So now we are talking about micro level products which are being used in and around our daily life. So this is a product which falls under 400 to 800 microns, right? I hope everybody recognize this. No, it is a medical syringe, which falls under 350 to 750 microns, and already being manufactured since a long time now, right? So nature is one of the best engineer. So this is a human hair, which falls under 70 microns, and somebody have maybe a larger diameter to that, and this is MEMS devices. Now we are talking in dimensions. It falls around 10 microns and above. I hope everybody have at least one device with them, whether it is a mobile phone or a laptop. So each and every device, they have at least one MES devices into that. So in a medical, further, we are talking about further less than 10 microns now. So now level which I am going to introduce a product or a technology or a manufacturing capabilities to you, which falls under this kind of dimensions. So it is a RBC, and you may be able to see, you can make a hole using this latest technology through which a single RBC can pass through. So micro machining is what, like, have you ever actually produced a micro machine part? This is the biggest question arise. In my career in last 20 years, I have seen a very less industries which have micro machining capabilities. They might have a single source of a single machine. It can be a single turning machine or a milling machine, or somewhat of a hybrid technology of turning and milling both. But when actually we talk about a micro hybrid machining center or micro hybrid manufacturing, very few of the companies or the institutes even they are using some technology into this. Why is this question arising? We will illustrate what is the is already taken into the agenda. So I'll let you know a few things about non-conventional micro machining processes, which are already available into the industry. And as I already said, MEMS devices are being manufactured. They are already being used, this kind of non-conventional micro machining processes. So photolithography on a silicon substrate, deep X-ray lithography, LIGA process in short form, and focused ion beam machining. All of these categories of manufacturing processes falls under micro machining, but they have biggest disadvantages. The main disadvantages is they are very lengthy processes. For each and every process, you need to develop a mold or a scalp, which is not easy to do that. You can easily find out the detail of each and every process. You can Google it, but I'm giving you in very short definition. Like, the major disadvantage is we cannot make a pure three-dimensional structure using these kind of processes, like, and the very low aspect ratio, and there's a limitation of the workpiece material, and the further they are very expensive to utilize. Maybe if I talk about a single source of this kind of non-conventional machining, they can go beyond 5 crores or so. So it's very difficult to manage that. So the second part is tool-based machining processes, which are the basic mechanical and electrical processes we can follow. So micro turning falls under that, micro grinding falls under that. They are the mechanical processes. Micro EDM, I hope everybody recognize the EDM. Because 20 years back it was difficult to find a EDM machine in India, but now everyone is using the EDM machine. So wire cut EDM is available and wire EDG is also available. They are following the electrical processes. So what are the advantages is already mentioned is less limitation of workpiece material, high material removal rate, and flexibility in 3D feature shapes. So we can easily, make a electrode or a 3D electrode or any profile electrode, and we can utilize it using a die sinking method, using EDM machine. And the high aspect ratio we can check, and capable of machining hard materials also. Even a tungsten material can be machined using this kind of, and the very low cost setups. They are not much expensive processes. So we have three kind of, largely we have two kind of multi-process machine technologies. One is a large conventional machine and other one is a ultra precision machines, right? But we are talking about a miniature multi-process machine tool, which falls within the both categories, and they have the major advantage for the micro machining. Using large conventional machines, they have some issues like mechanical and thermal deformation. You cannot avoid chatter, vibration, tooling, and clamping errors. Like even you are using any kind of fixtures, occupying large space and higher power consumptions. They are not even suitable for the ultra precision parts. Now, on the other hand, like ultra precision machines, they are excellent motion accuracy, extremely expensive, and require regular maintenance, occupy large space, and higher power consumptions. Mostly not suitable for the hybrid processes. As I already told, if you want to use ultra precision machine for turning or milling, a single process, you can utilize it. When we are talking about a hybrid machining, so number of setups should be very less, because if you try to change any tool or any fixture, you will not get that kind of accuracy what is it is required into the micro machining. So as I already told, the miniature multi-process machine has more advantage for that. They have higher accuracy, less number of setups. On a single setup, you can, without changing a tool, or you can create a tool itself on the machine and utilize it. You can manufacture a tool using a turning technology and utilize the same tool for doing as an electrode for the die sinking. So less number of setup, minimum idle time, significant reduction in investments, reduced power consumption, and required floor space. They are very compact. So minimize thermal expansion as well. Advanced sensors and instrumentation for superior positional accuracy are being utilized. Fast mechanical response time they have, and flexible of hybrid micron fabrication is also an advantage for that. So any question until now? So what exactly is micro machining? So we are talking about a hybrid micro machine tool, which is already available in the industry, and mostly in the research institutes like IITs and IITs. It is already being available now. What it does basically, it is a single source of machine. It's a single source of setup, which can run a micro turning, micro milling, micro drilling, micro EDM milling, micro EDM drilling, micro wire EDM, and micro wire EDG, and micro reverse EDM also. And now the latest innovation into this product is they had incorporated the laser technology also, which was earlier not available. So they had already introduced the laser technology, and that product is already being delivered in IIT Ropar. Recently, we have delivered that product and being installed. So IIT Ropar is a single institute. They have this integrated laser technology available into that. So hybrid micro machining tool has a capability of 3-axis continuous CNC fully closed loop. So just like a standard state of art conventional machine, a fully closed loop feedback makes precise motion control feedback possible. Like we can work on a very precise level. So on machine measurement, we can mount a 60x camera on the machine itself, through which we can digitize, we can measure, and we can record what is happening on the machine, like the cutting and each and everything. It can be recorded, right? And the positional accuracy of this machine is plus minus 1 micron per 100 mm. Getting accuracy is not a big deal, but carrying it on certain length, it is the biggest issue. So up to 100 mm, you can get accuracy of plus minus 1 micron out of this machine. Normal conventional machines, if you talk about a simple CNC like milling or turning machine, they work under the accuracy of 25 to 100 microns. So this is a kind of difference you can check. So resolution is 100 nanomicron. Electrically isolated spindle. As I already told you that you can make your electrode using the other machining processes like turning and milling, and the same without unmounting that workpiece, you can use it as an electrode for the EDM purpose. So this isolated spindle is basically a patent product, which is a research has been done in Singapore University. So this is our core base of this research. And spark control mechanism is already there, and it is a very modular design. It looks like a simple any you can check the kind of close enclosure having a control panel on it. You can create your own program, NC program, and you can transfer that program through using any RS-232 or RJ435 connectivity. And even you can utilize your pen drive also. You can use any CAM software. You can create a program, whether it is a turning or whether it is a milling, and you can transfer it to, right? And a spindle with a negligible runout, because this has to be done, otherwise the accuracy cannot be managed. So this is the world's first hybrid micro EDM. And the product name is DT110i, and it's a very the design is very simple way. Why I'm showing you this, because this is a kind of technology which will give you a bigger scope of the research. The people they are using, the founder, who is the founder of this machine, has already published more than 600 papers. He has already published more than 600 papers out of it. Little bit about the construction of this machine is basically it's a natural granite table is being used with the base, and the y-axis module is mounted on the granite base, and x and z axis are mounted on gantry type cast iron structure, which is also mounted on granite base. And the XYZ travel of this machine is 200 by 100 and 100 mm. Because we were talking about a micro machining, manufacturing. So the table size is not a bigger. As you can see, see, this is a microscope or a camera can be mounted on this machine, and this tank can be utilized for the EDM part as well. And anytime it can be, unmounted from the table. And the best part is only a single screw is being, utilized to mount and unmount any kind of structure out of it. Okay. So, why and how this micro machining research has been done? It is a very great story behind it. I'm just sharing with you because the the founder or the innovator is already from such institute. So I hope everybody recognize Panasonic. A long back in mid 90s, Panasonic is looking for manufacturing support to manufacturing 40 micron electrode. They required it for some of their manufacturing purpose. Actually, they have to make a hole of 50 microns. So for that, they are looking for a support to make a electrode of 40 microns in the mid 90s. Professor Rahman is the founder of this company, Microtools, and he's an innovator of this micro machine. He was there in Japan at that time, and he has been called for the support. And what was the current setup of the Panasonic? They were using different machines, right? So for making this electrode, they are using three machines to do it currently. The first dressing electrode to 40 microns using EDG and measuring 40 micron on CMM. And finally making the hole using EDM die sinking. And the average time they were taking is around 8 hours to do one hole basically. The reason being the handling errors. Imagine handling something half the diameter of hair. It is it's not easy task. So they wanted to make many holes for that. So they have been called upon Professor Rahman, and Professor Rahman has taken up the initiative, and he said, "Okay, I'll do that. Why not? It can be done." So that kind of challenge he has taken, and the challenge is making a diameter of 15 micron hole on a SS sheet. So that was a challenge. So EDM die sinking tool requirement, electrode of diameter 45 micron is required. So initially available workpiece were brass, 4 mm dia and 6 centimeter long. So approach has been taken is micro turning workpiece and EDM die sinking. So this approach they had decided to go through. So step one was the diameter reduction to 100 micron using micro turning, and step two was further diameter reduction to 50 microns. So what was the challenge? The why turning of shaft below 100 micron is so difficult? Because the most serious problem, cutting force. So it has, as you see, the two components. So they tried and they calculated each and everything, and so this shaft has been created the below 100 microns. So they have observing all the cutting force parameter by taking the consideration deflection and stress equations. They tried varying all the possible parameters so that the lowest possible deflection and stress are achieved in hope to achieve shaft below 100 microns. But the problem persists. Their research then led them to paper on micro turning by a German professor who suggested that step turning can be utilized to desired diameter. So now they have two type of tool paths. The path A is a regular type of path. It's a regular type of turning used in turning, CNC turning, and the path B is a step turning. So they utilized the step path B. Because in path B, this is a step cutting, and this method is a very small length of cut is chosen, maybe 50 microns. Then a similar depth of cut is chosen. Now first cut can be 50 micron and the length of 50 microns, and second cut is the same length, but depth can be vary for 100 microns. So using this, surprisingly, this process yield amazing result, and diameter of up to 60 micron were being achieved. As step size reduced, the deflection and step error reduced. So easily you can check out through this equation. So now we have a shaft of diameter of 50 micron. As earlier we have a 100 micron shaft. But remember, correct, our aim was to make a electrode of diameter 40 micron. So step turning also 60 micron was achieved. This time professor said, why don't we eliminate cause of deflection, the radial force on workpiece. So when vertical turning happens on the machine, in an ideal world, the radial force exerted on the workpiece by tool should be 0, and only thrust force in axial direction should be there, as shearing and chip removal happens. So, so the idea of using a cutting tool with sharp tip arise, and they further achieved the lesser diameter. So they utilize the solution again laid in the machine built as it was capable of micro EDG, the operation as well. The PCD is constructed with cobalt, with being electrically conductive makes EDG possible. So the team did the EDG machining and fabricated the modified PCD cutter of diameter of 5 microns. So we were talking about the 14 micron, 45 microns, and now we have achieved the 5 microns. So this is the step of micro turning processes they have utilized. Earlier the diameter is for the 4 millimeter, and the final shaft has been achieved. So micro turning capabilities, if you check a hair of below, and a 11 micron graphite shaft is being manufactured using this technology. Further, so these are the practical photographs has been taken after manufacturing, all the steps. Using 5 micron shaft, EDM was done, and the world's smallest hole using micro EDM was fabricated on the same machine of just 6.5 microns. So machining a 50 micron hole initial electrode, dimension 4 mm and 6 mm. And this was the difference. The tool set up in conventional EDM already explained, and tool setup in hybrid micro EDM, because on the same setup we had manufacture a tool, and the errors are very less, and this spindle of workpiece placed within the EDM tank without removing the electrode, because the same table is being utilized. So the question may arise, why combine micro EDM with micro turning? So micro turning can offer fast re-preparation of tools, better rigidity, no reclamping errors. So this is the major benefit we can get over there. So this is really a micro hybrid machining. We are not only talking about a micro machining processes, but we are more keen to talking about the micro hybrid machining setups. So I hope importance of hybrid processes of micro machining are understood. Now there are many other processes possible due to these are some samples which has been made using micro milling, micro fins of 70 micron thickness. Sorry, I think some error of font is there. Sorry, it's a micron. That symbol has to be micron. Some font error is there. Sorry,
What is this used for?
it's used for like the different kind of industries. This is more like of an impeller type of product. Can be utilized in the aerospace industries as well. It's very small.
Very small.
It's very small.
So this
Yeah.
aerospace.
See, I'll be sharing what kind of application can be utilized using this kind of technology. It has been made as a sample in a medical industry being utilized. See the next part, the very small fins being manufactured using the same technology. It's a micro milling. This is what we are talking about, the smallest holes. So this after the development of this micro machining process, so these kind of processes can be done. I think it is not visible over there, right? Right. So micro EDM die sinking can be done. Micro milling, as already written. Micro reverse EDM is like I'll show you some example of that. This is a reverse EDM can be done. It is a patent technology of micro tools. It is understood that finishing operations are rarely possible. Hence, our EDM itself is designed to generate the highest quality finish and the dimensional accuracy. As I already explained, the process of making electrode and utilizing it on a workpiece. The similar way it has been shown. The first specification of electrode can be, utilized, and further the same spindle is working for the EDM part. So this is the technology which is available. This is micro wire electrical discharge machining attachment, which can be mounted on this machine, and as a separate attachment to itself. The spindle itself is removed from the Z axis, and the wire EDG picture can be added. This is a different from conventional wire EDG because the diameter of wire is very small. So normally diameters are being utilized more than 200 microns and above. But here we are utilizing 30 to 70 micron diameter of the wire. So this is another attachment. So there are more sample for this CDM machine. It's micro wall slot. This is another sample. This is the reverse EDM, which I already told you. Earlier, we need electrode to make a hole, and this is the reverse process. So what are the major application areas? In aerospace, for the turbine parts, fuel injectors, calibration tools, the micro machining has been done. And for making a micro molds, this technology can be utilized. And the medical, they are very large, vast field area to manufacture a lot of components. Uh, and even in electronics and microelectronics. And for the academic part, the internal research purpose, it can be utilized, and consultancy and fabrication job purpose can be fulfilled. There are the more applications. You see the dental orthodontic spring with a nickel and titanium material. And the textile, the micros spinneret and micro nozzle of various dimensions. And as I said, the micro mold can be manufactured. So I can directly take to you the working model of this machine. I will show some video. As I told you, this is the camera mounted on the machine, and all the pictures has been taken through this only, and we can record it uh, through live machining as well. Otherwise, it's very difficult to check what is happening on the machine because it's very micro level. So as you see, the electrode has been made, and the similar electrode is being used for the EDM purpose. So this is a laser technology which has been integrated very recently, because some of the customer they required a fastest technology method. So this laser has been incorporated very recently, and these are the parameter of the laser technology: extremely high cutting speed, high depth of cut, and highly material versatility. And disadvantage maybe requires subsequent finishing because of the laser cutting. We may need to be some post machining or finishing operation may be required. And we can utilize spindle speed between the range of 10,000 to 60,000 RPM. We can utilize in a normal in industry. If you talk about CNC machines, so the availability of spindle speed is around 8,000, 10,000, and which are easily available. But we can work out up to the 60,000 RPM. So more the RPM, more the finishing can be achieved. And the dynamometer is all can be mounted on the machine to measure the micro forces, and we have a vibration device also, and ultrasonic cleaning device can be utilized. So this is all about the technology which we have available, and a lot of institutes are using this technology, and a lot of research papers are being published using this technology. And about Microtools is basically a Singapore-based company, and it is a spun out of a national university of Singapore, because Dr. Professor Rahman is the founder, and he is still a professor over there in Singapore University. And they are the developer of micro and nano precision machine tools, and which are research oriented, and they have better technologies, pioneer of hybrid micro EDM machine tool technologies. And they have global presence, Singapore, Malaysia, and globally they are already sold out a lot of machines, and mostly they are using into research purpose. This is the latest model of the machine. In video, you must have seen older structure than the enclosure. This is the latest structure of this machine. And there are two machines. One is hybrid micro machining center, and the second one is ultra precision diamond turning lathe. But this is an independent machine for turning purpose only. It is a lathe. More about this hybrid machining center. As I said, we are using a very user interface. It's a very user-friendly interface we are utilizing. I hope most of the people out of you are aware about the CNC machines. The basic part is when we mount any workpiece on the machine, we need to give a reference to the machine. So we have to decide the machining coordinate system, because any machine, any CNC machine, they have their own home position, and we need to define the machining coordinate system as per the workpiece. So in this machining center, it has been done in a very easy way, and the sensors are being utilized, and on a single button you can define the MCS and to start the machining activities, whether it is a milling, turning, or any kind of etc. So it is very easy. You can make a program. You can make a program and run immediately. So this is the EDM power supply integrated in the system. Before I conclude, if you have any question. I think so this is a spark laser technology which has been incorporated recently. Change. Can you change? Sorry. This is the added feature. Recently, as I already told, we have supplied this to IIT Roopur recently. Last month. Yes. You need to change the head, the spindle part, and you have to replace it with the laser technology. And a lot of other things need to be required. So it is, yeah. It's recently it has been done, especially for the IT, but now it is already incorporated and it is available.
This in the subsidies is mainly for this testing purposes. products are listed.
No. Already they're using for, it is not a for the production side. You can say it's for the production side because it is a micro and we need more patience to manufacture a single part for that. But yes, for the research part, a lot of things, people, most of the research recently in IIT Kharagpur, someone has developed a new material which is anti-slip. Yeah, it's anti-slip material. He had done his research using this machine. In IIT Ropar, they are utilizing it for the forming part. So microforming, they are utilizing this machine. So there are endless. Yes, if you go and Google Dr. Professor Rahman, they have his own blog available on. I can share the information. Just write down micro tools and Professor Rahman. That's it. You will find out his blog. All the research paper and whatever he has published, each and everything is available. Yeah. Professor Rahman. Yeah. He's an Indian origin, but he is being settled in Singapore now. He's still a professor at Singapore University. He come once in a year in India, but at that time, I think recently he's coming in NIT Jalandhar. There's a international level conference is being organized. So he's a key presenter over there.
Any query from JCRC University? JCRC Jaipur?
Hello.
Yes, sir.
Madam, sir, one query is that what are the role of these new automation technique like in miniature gear? If you want production of miniature gear, then how can we implement these conditions, steps?
So miniature gear can be manufactured using wire EDM as already shown. It's already shown on wire EDM. Have you seen into the video?
Yes, sir. But the main thing is that what is the accuracy and precision required to product?
Accuracy is already being maintained, as I already told you that it's plus minus 1 micron. That accuracy is already being maintained.
Okay, sir.
Right?
Okay. Thank you, sir.
Okay, welcome. So for any further query, you can directly go on to microtools.com and each and everything is mentioned there. And you can Google for the research paper for the micro EDM. This is the latest subject has been utilized for the research purpose also. A lot of people they are working on the same. They are doing their PhD on this micro EDM itself. And Professor Rahman, I must request you all. You can at least Google once for the Professor Rahman. He is the pioneer into micro EDM technologies, and he has his own blog, and you can find a lot of information over there. So maybe today you don't have any query, but if you Google and you will find a lot of things. Thank you very much and being patient, and you are always welcome. You can have my detail as well. You can write on my email ID and my number, and you can anytime. You are welcome. My email ID is s.bhardwaj, BHARDWAJ @ldspl.com. dspl.com. It is basically our company, Lucrative Design Solutions Private Limited. Same. And for this hybrid machining center, microtools.com is our website. We are the Indian partner for this product. Company is working since last. They started their venture in 2003, and in 2006, first machine has been installed in IIT Bombay. IIT Bombay was the first product, and now we have already been installed more than 40 machines. IIT Bombay, then MNIT Jaipur, they have. Punjab Engineering College, Chandigarh, they have the machine in Chandigarh. IIT Ropar, I already been told. IIT Patna, they have the machine. Sorry? In southern part, yes. Yeah. You can give me your detail, I can share. Because I'm taking care of the north. So definitely, IIT Kharagpur is one. They have the machine. And Pune, they have. I think. Sorry? IIT Chennai, CPET Chennai, they have this machine in Ginde. They have this machine. Although they ordered for the 3 machines, but because of that tsunami came and everything spread it out. But they have one machine which is working.
What's the average cost?
Average cost is around 2 lakh Singapore dollar. The basic, the base of it. And we go beyond 3 lakh Singapore dollars. The Indian, you can calculate, started with 90 lakhs. Start by that.
So, any production machines are still?
We are already working. We are already working for the production level of setups because presently we are covering the institute level, but the next year we have a plan to cover the industry. In US and Japan, yes, this machine is being utilized for the production part as well. So we are already working on that. Maybe we are recommended to the company some part of the machine will be manufactured in India in future. Some part of that machine. That can be a great part for us. Okay, thank you very much.
Hello.
Thank you all the members of the call is a day and tomorrow will be assembled again at 10.